Welcome to the Sleepy Cosmos channel, a place where science and serenity meet. Here we explore the quiet wonders of the universe, from dark matter to string theory, all told in a calm, soothing rhythm designed to help you relax, drift, and dream among the stars. Each video is a guided journey through the cosmos, slow, meditative, and filled with real science wrapped in gentle storytelling. So if you love space, curiosity, and the peaceful side of knowledge, you're in the right place. Make sure to subscribe for more new sleep narrations every week. And if you'd like to reach out for collaborations or business inquiries, you can contact us at the sleepycosmoschannel@gmail.com. Now, settle in, take a deep breath, and let's drift into the universe together. Tonight, you are simply drifting through a quiet space where curiosity softens into calm, and the universe becomes a gentle companion instead of a puzzle to solve. You are listening to a slow exploration of the multiverse, a possibility that stretches far beyond the boundaries of our familiar cosmos, yet arrives here tonight not to challenge you, but to soothe you, to remind you that even the largest mysteries can be approached with softness. The word universe often feels absolute, as if it must contain everything that exists, every particle, every field, every moment of time. But in modern physics, the word may describe something smaller, something local, something shaped by specific conditions that might not be unique. Scientists use the word universe, the way travelers use the word horizon, as something that appears complete only because we cannot see beyond it. Our observable universe, the region from which light has reached us since the beginning of cosmic expansion, is only a small portion of a much larger whole, perhaps a very small portion. And tonight, you are invited to rest with that idea, without pressure, without analysis, just drifting alongside the thought that the cosmos might be wider than we can imagine. The multiverse is not a single theory, not a single picture, not a single claim. It is a family of possibilities, arising naturally from the mathematics that describe space, quantum fields, and the deep structure of reality. Physicists do not reach for the multiverse because it is dramatic. They reach for it because certain equations, when followed gently to their conclusions, suggest that our universe might be one thread in a larger tapestry. Tonight, you will not need to follow the equations, only the calm shape of the ideas behind them. Imagine space-time as a vast landscape, smooth in some places, twisted in others, expanding in ways that our senses cannot fully grasp. Imagine regions of this landscape separated not by walls but by sheer distance, so far apart that their light will never reach one another, not even in the lifetime of the universe. To an observer inside one region, that region feels like the whole. But to an outside perspective, if such a perspective could exist, the cosmos might contain countless isolated domains, each with its own conditions, its own flow of time, its own structures. In this quiet moment, you can let your mind rest on that mental image, not trying to build it precisely, just letting it drift around the idea that our universe might be one room in a structure with many rooms. Scientists consider this seriously because of cosmic inflation, a rapid expansion that seems to have occurred in the early phases of the cosmos. Inflation smooths space, stretches it, and in many models, creates multiple regions that stop inflating at different moments. Each region becomes a universe of its own, with its own initial conditions, its own cosmic story. Not a fantasy, but a natural consequence of the mathematics behind the inflationary field. You don't need to hold the mechanics tightly. Just feel the broad idea, like watching bubbles rise slowly through a calm sea, each bubble separate, each bubble complete. Quantum physics brings its own form of multiplicity, not chaotic, not overwhelming, but quietly branching. Every physical system exists as a wave of possibilities, a superposition of outcomes, until interactions with the environment cause those possibilities to separate, forming distinct, non-communicating branches. To the many worlds viewpoint, each branch is real, each outcome unfolds in its own history, and the universe becomes a gently dividing river, splitting and flowing softly into new channels. Tonight, you don't need to decide whether this view is correct. You are only invited to let the concept drift by, a calm image of reality unfolding into many paths. Other possibilities arise from deeper theories of physics. In some models of high-energy fields, the laws we know may not be fixed everywhere. Different regions of space-time might settle into different stable states, with different strengths of gravity, different masses for particles, even different numbers of dimensions. A cosmic landscape of possibilities, each region shaped by its own physical rules. You do not need to imagine these universes clearly. Just sense the overall idea that the laws we experience might be one option within a space of many options. The size of the cosmos also invites the idea of multiplicity. If space is infinite, then patterns must eventually repeat. Atoms arrange themselves in only so many ways, and given infinite volume, those arrangements reappear, sometimes nearly identical. Sometimes exactly so. Somewhere, extremely far away, there could be a region with another Earth, another pattern of stars, another person thinking thoughts like yours. This is not speculation from fiction, but a mathematical consequence of certain models of infinite space. But tonight, you don't need to hold the mathematics. You can simply let the thought float by, gentle, unhurried, like the reflection of a distant galaxy on still water. Other ideas suggest that our universe may be a three-dimensional slice embedded in a higher dimensional structure. In these models, other slices could exist nearby, parallel to ours, separated not by distance, but by dimension. These parallel worlds would be invisible to us, yet profoundly real. Their gravity might leak faintly into our own, their existence hinted at through the strange weakness of the gravitational force. A calm image, sheets of cosmic fabric drifting in a larger space, each one a separate universe. Some hypotheses go further. Not that reality is an illusion, but that reality might be emergent, built from deeper informational rules, a kind of quiet computation, not cold or mechanical, but structured and consistent. In this view, the universe behaves as if it is processing information. Patterns unfold according to rules. Complexity emerges from simple interactions. This does not diminish the cosmos. It simply offers another possibility, that what we perceive as physical might arise from something even more fundamental. Tonight, you do not need to choose among these ideas. You only need to drift with them. And in the end, there is the quiet recognition that some questions may remain beyond measurement. Cosmic horizons limit what we can see. Quantum limits prevent us from observing other branches. Mathematical limits restrict what can be proven from within a system. The multiverse is not an escape from understanding. It is a reflection of the boundaries built into understanding, a gentle horizon beyond which possibilities continue. The purpose of this narration is not to answer the question of whether the multiverse is real. Tonight is not about conclusions. Tonight is about rest, about easing into the largest ideas in science with a calm and steady rhythm. You are here to drift through possibility, to feel the vastness without needing to grasp it, to know that the cosmos can be enormous, mysterious, and still gentle. Let the mind settle into curiosity, and let curiosity soften into calm, as you drift deeper and deeper into the quiet spaces between worlds. In the quiet stillness of thought, it becomes possible to look at our universe not as a closed and final structure, but as something that may be part of a greater expanse. Tonight, the goal is not to come to conclusions, but to drift calmly through the scientific reasons, the analytical reasons, that have led physicists to believe that our universe might not be alone. Not through fantasy, not through imagination untethered, but through mathematics, observations, and the quiet logic of cosmology. When scientists speak of the multiverse in a serious way, they rarely mean parallel worlds layered beside us like pages in a book. They are usually referring to something quieter, something rooted in physical processes we already understand. The first of these processes, and perhaps the most important, is cosmic inflation, a period of extremely rapid expansion in the early universe, so brief that it would be easy to overlook, yet so powerful that it shaped everything we see. Inflation stretches space at an exponential rate, so fast that distant regions move beyond each other's horizons. When this happens, those regions can no longer communicate, no longer exchange light, no longer share information. To an observer inside one of these regions, that region becomes their universe, a complete domain with its own observable structures. But inflation does not end everywhere at the same moment. In most models, it ends unevenly, dropping out in patches, like small clearings forming within a fog. Each clearing becomes a universe, a pocket of space-time with its own cosmological properties, a bubble emerging within a vast inflating medium. The mathematics behind inflation does not force the creation of one universe. It naturally produces many. The reason this is taken seriously is simple. Inflation explains observations that no other theory explains as cleanly. The uniformity of the cosmic microwave background, the distribution of density fluctuations, the large-scale smoothness of space-time all align with inflationary predictions. And inflation, almost reluctantly, suggests a multiverse. A single inflating region can generate countless pocket universes, each one isolated by distance so vast that their light will never reach one another. The observable universe is only one such pocket, a bubble within a sea of expansion. And tonight, you can let that idea drift gently through your mind, like a soft current of possibility. There is a quiet distinction that scientists make, one that often goes unnoticed. The observable universe is not the entire cosmos. The observable universe is only the region from which light has had time to reach us, since the earliest moments of cosmic expansion. A sphere, finite in size, not because the cosmos ends there, but because our ability to see ends there. Beyond that boundary, space continues. Galaxies exist, structures form, cosmic evolution unfolds. But the light from those regions has not yet arrived and may never arrive. If the cosmos extends far beyond this boundary, and if inflation operated the way many models suggest, then distant regions of space may have conditions so different from ours that they effectively function as separate universes. Their temperatures, their densities, their vacuum states may have settled into different configurations. In that case, our universe is simply one region of a much larger whole, a room within a structure of many rooms. This larger structure arises from a simple observation. Fields that permeate space can settle into different states. Just as water can freeze or boil depending on conditions, the fields that define physics can fall into different stable configurations. These configurations determine the strengths of forces, the masses of particles, and even the dimensionality of space. Inflation can distribute different regions into different states, creating domains where the laws of physics appear distinct. Not imaginary laws, not fictional laws, but different solutions to the same underlying equations. Our universe is one such solution, one stable region within a broader landscape. The idea may seem vast, but it is rooted in the mathematics of how fields behave. Gently, you can let that idea settle. There is no need to picture the entire landscape, only the possibility that other regions exist. Another reason physicists consider multiple universes comes from the horizon problem, a problem solved elegantly by inflation. The horizon problem asks, why is the universe so uniform? Why is the temperature of the cosmic microwave background the same in regions that are so far apart that they could never have exchanged light? Inflation answers this by beginning with a small, uniform region and expanding it to enormous scales. Regions now separated by billions of light years were once close enough to share information. Inflation stretches this once uniform region into the large-scale structure we observe, and the same mechanism, the same expansion, can create multiple such regions. Each region uniform within itself, each region separated from others, a cosmos of isolated but internally smooth domains, a multiverse born not from speculation, but from a process designed to explain observations. And yet, inflationary models go even further. In many versions of inflation, the expansion never fully stops. It continues eternally in some regions, while ending in others. This process is called eternal inflation. In eternal inflation, pocket universes continue to form endlessly, each one emerging from a region where inflation has stopped, while the surrounding space continues to expand. This creates a fractal-like structure of universes, each one isolated by ever-growing distances, each one with its own physical properties. Our universe is one bubble in this fractal sea, and there may be countless more. To rest with this idea, you do not need to imagine each universe individually. You only need to sense the calm logic behind it. Inflation predicts multiple universes because it predicts uneven endings. Quantum fluctuations in the inflationary field cause different regions to exit inflation at different times. This is not an added layer of speculation. It is a mathematical consequence. A gentle conclusion emerges. If inflation happened, a multiverse is likely. not dramatic or fantastical, but simply large. Larger than our senses, larger than our observable sphere. Another foundation for the multiverse comes from symmetry breaking. In the early cosmos, forces may have been unified. As the universe cooled, these forces separated into the four we know: gravity, electromagnetism, the strong force, the weak force. But the way they separate depends on conditions. Regions with slightly different initial states could settle into different configurations, different strengths, different vacuum energies, different cosmological behaviors. Inflation magnifies these differences, separating regions into distinct domains. One region may form stars, another may not. One region may allow chemistry, another may remain empty. These differences arise naturally from the mathematics of fields and symmetry. A multiverse of physically distinct regions becomes not only possible, but likely. Physicists also examine the scale of the cosmos. If space is infinite or even extremely large, then distant regions may be forever inaccessible. Not because they do not exist, but because the expansion of space carries them away faster than light can bridge the distance. These regions cannot interact with ours. Their physical conditions evolve independently. They become effectively separate universes. This is not a different theory. It is a simple consequence of expansion. A quiet understanding: separation by distance can be just as complete as separation by dimension or by physical law. Tonight, drifting through these ideas, you can feel how the scientific roots of the multiverse are not built on imagination alone. They emerge from theories that already explain observations. Inflation explains the smoothness of space. Symmetry breaking explains the variation of forces. Quantum fluctuations explain the structure of galaxies. Large-scale expansion explains cosmic separation. And woven through all of these explanations is the quiet, analytical suggestion that our universe may be one region in a larger whole, not for the sake of fantasy, but for the sake of consistency. The scientific basis for the multiverse is calm, methodical, and rooted in observed phenomena. It is not a leap into the unknown, it is an extension of the known, a gentle widening of the frame through which we see the cosmos. As you rest with these ideas, you can let them settle like soft dust across the mind. No urgency, no pressure, only the quiet possibility that reality may be broader, deeper, and more varied than our single universe suggests. And with that calm thought, you drift forward into the next questions that science invites us to explore. As you drift deeper into these ideas, the scientific reasoning behind the multiverse continues to unfold, calm, steady, analytical, like a slow tide moving across the mind. Inflation remains one of the strongest foundations for this possibility, but it is only one part of the broader landscape of evidence. To understand why so many physicists take the multiverse seriously, it helps to look at how different pieces of modern cosmology fit quietly together, forming a picture that is larger than any single observation. One of the most important insights comes from measurements of the cosmic microwave background. This faint radiation, a soft glow left over from the early universe, carries detailed information about the structure of space-time. The temperature variations across this background are incredibly small, yet they hold a precise fingerprint of the processes that shape the cosmos. Inflation predicted these patterns long before they were observed. The smoothness of the temperature, the distribution of fluctuations, the scale at which those fluctuations appear, all match what inflationary models describe. This alignment between prediction and observation gives physicists confidence that inflation is more than a mathematical curiosity. It suggests that inflation in some form actually occurred. And if inflation occurred, then the possibility of multiple inflationary regions follows naturally. Each region produced by inflation has its own observable boundary, its own cosmic horizon, its own story, its own structures, and perhaps its own physical laws. The scientific picture begins to resemble a quiet collection of isolated domains, separated not by walls, but by vast differences in location and time. Another reason scientists consider multiple universes is the behavior of quantum fields in curved spacetime. The vacuum of space is not empty. It is filled with fields that fluctuate constantly, producing pairs of particles and antiparticles that emerge and vanish. During inflation, these fluctuations are stretched across large scales. Small variations in the density of energy become amplified, creating the seeds of galaxies, stars, and clusters. These amplified fluctuations also influence how inflation ends in different regions. A slight variation in the energy of a field, a tiny difference smaller than any measurement could detect, can cause one region to stop inflating, while another continues. These tiny variations create a patchwork of endings, a mosaic of universes. From the perspective of physics, this mosaic is not speculation. It is a quiet outcome of how quantum fields behave under extreme expansion. This is why inflation does not simply allow a multiverse. In many models, it requires one. There is also the question of fine-tuning. Physicists do not invoke fine-tuning lightly, but certain parameters in our universe appear extremely precise. If the strength of gravity were slightly different, stars might not form. If the mass of the electron were slightly larger, atoms might not be stable. If the expansion rate were just a little faster, matter would never have clumped into galaxies. These conditions are not arbitrary. They arise from the fundamental constants of nature, and yet they fall into a narrow range that allows complex structures to exist. One explanation for this fine-tuning is that our universe is one region of a larger multiverse. In different regions, the constants may vary. Most regions would not form stars or planets and would remain empty. But in a few rare regions, conditions would allow structure, chemistry, and life. This idea is not presented as a final answer. It is simply a possibility that emerges naturally from models where physical laws vary across space. A quiet understanding follows. If the multiverse exists, then the fine-tuning of our universe is not surprising. We live in a region where conditions allow us to exist. Regions without these conditions simply remain unobserved. This does not prove the multiverse, but it removes the need for extreme precision in the laws of physics and aligns with what inflation and quantum fields already suggest. Another analytical point arises from the limits of causal contact. If the universe is expanding faster than the speed of light at large distances, and it is, then every moment more regions slip beyond our ability to see. These regions are not destroyed. They do not vanish. They simply move out of reach. From a scientific perspective, regions that can never communicate, regions that evolve independently, regions whose light will never reach us, function as separate universes. Their histories unfold in isolation. Their structures grow without influence from ours. This is not a philosophical argument. It is a physical one. If cosmic expansion continues indefinitely, the number of independent regions will grow without bound. Each one becomes its own universe, separated not by dimension, but by the relentless stretching of space. The cosmos becomes a vast collection of ever-expanding domains, each with its own horizon, each with its own observable story. There is also the subtle question of vacuum stability. Quantum field theory suggests that the vacuum state we inhabit may not be unique. Fields can have multiple stable or metastable configurations, separated by barriers of energy. In a high-energy environment, such as the early universe, these fields could settle into different vacua in different places. Each vacuum corresponds to a different set of physical laws. In one vacuum, particles have one set of masses. In another vacuum, those masses differ. In one vacuum, certain forces may be stronger or weaker. In another, the number of stable particles may change. Inflation, through its enormous expansion, can isolate these regions permanently. Once separated, they evolve independently. No signal can pass between vacua once inflation has driven them apart. A multiverse of vacua emerges, not from imagination, but from the mathematical structure of field theory. Again, not proof, but a quiet, analytical consistency. There is another reason this idea is taken seriously: entropy. The second law of thermodynamics tells us that entropy tends to increase. But on the scale of the cosmos, entropy behaves differently. Regions of low entropy expand and evolve into complex structures, while regions of high entropy remain simple and featureless. If the universe contains many regions, then statistically, some will begin with low entropy. These regions can form galaxies and stars. Most regions will not. The existence of our low-entropy universe becomes less surprising if the cosmos contains countless regions with different initial conditions. Our region is simply one of the rare locations where complex structures arise. This line of reasoning does not require speculation. It uses established principles of thermodynamics applied on a cosmic scale. As you drift through these ideas, you may notice a pattern. Each scientific motivation for the multiverse comes from different areas of physics, yet they all point gently in the same direction. Inflation suggests multiple domains. Quantum fields suggest multiple vacua. Cosmic expansion suggests isolated regions. Thermodynamics suggests multiple initial conditions. Fine-tuning suggests a landscape of possible laws. These pieces do not form a complete picture, but they form something meaningful, a quiet mosaic of possibility. And in this mosaic, the idea of a multiverse is not an outlier. It is a natural extension of what we already understand. The next idea to consider is scale. The observable universe is about 90 billion light-years across, but there is no reason to assume the cosmos ends there. It may continue far beyond what any instrument can detect. If the cosmos extends 1 trillion times further, or 1,000,000 trillion times further, or extends without limit, then the number of independent regions becomes unimaginably large. Each region evolves separately, each becomes its own universe in practice. This is not a fanciful idea. It is simply the consequence of accepting that the cosmos may be much larger than the region we can see. Even conservative cosmological models allow for an enormous extension beyond the observable sphere. In some models, the cosmos could be effectively infinite, and in an infinite space, the number of possible configurations becomes infinite as well. A quiet conclusion emerges. A large or infinite cosmos behaves like a multiverse, even without invoking deeper theories. As this section approaches its end, the scientific motivations for the multiverse can be seen as interconnected, forming a framework that is gentle, analytical, and grounded in known physics. None of these ideas require abandoning established science. They extend it carefully, logically, following equations where they lead. And where they lead is to a cosmos that may be far larger, far more varied, and far more intricate than the universe we observe. A cosmos composed not of one domain, but of many. Not a single stage, but a collection of stages. A quiet expanse, filled with isolated but real regions of space-time. As you rest with these thoughts, you can let them drift softly through the mind, without pressure to conclude, without urgency to decide. Simply floating with the possibility that the scientific picture of reality may be broader than the single universe we know. The scientific picture of a multiverse becomes clearer and gentler when we look closely at the structure of space-time itself. Even without invoking exotic theories, space-time has properties that naturally give rise to isolated regions, regions that behave like separate universes. And as you drift deeper into these ideas, you can feel how each concept unfolds calmly, one after another, without urgency, without pressure, just the steady rhythm of analytical thought. Space-time is not static. It stretches, bends, curves, and evolves. General relativity describes this behavior with remarkable precision, but it also reveals something subtle, something easy to overlook. When space-time expands, regions separate faster than light can travel. This expansion does not violate relativity because it is space itself that stretches. There is no rule against distances increasing faster than light. As expansion continues, distant regions slip permanently beyond one another's horizons. Light can no longer travel between them. Information can never be exchanged. They become causally disconnected, forever isolated. From a physical perspective, these isolated domains behave as separate universes. Their galaxies evolve independently. Their cosmic histories unfold without influence from ours. The boundary between these regions is not a material wall, but a horizon created by expansion. Even in the simplest cosmological models, this isolation occurs naturally, and with inflation, the effect is magnified dramatically. Inflation not only creates isolated domains, it creates domains with slightly different initial conditions. Quantum fluctuations ensure that no two regions exit inflation in exactly the same way. Tiny variations in the energy of the inflationary field, variations far smaller than anything we could ever measure, become stretched across enormous distances. In one region, inflation ends a little earlier. In another, it ends slightly later. In one region, density fluctuations produce more clusters. In another, they produce fewer. These subtle differences become the seeds of entire universes, worlds shaped by the smallest imaginable variations, amplified by the growth of space-time. This is not speculation layered on speculation. It is a quiet consequence of quantum uncertainty applied to cosmic expansion. There is another quiet motivation for the multiverse, one that emerges from the nature of fields themselves. The fields that define physics, electromagnetic fields, Higgs fields, inflationary fields, and others, do not always have a single lowest energy state. Some have multiple stable configurations, separated by energy barriers. These configurations are called vacua. In one vacuum state, the laws of physics take one form. In another, they take a different form. The forces behave differently. Particles have different masses. The entire structure of physical law shifts. During inflation, different regions can fall into different vacua. Once separated, they remain isolated forever. Each region becomes a universe with its own physics. This possibility arises directly from field theory, especially in models involving scalar fields. And scalar fields are not hypothetical. They include the Higgs field, whose existence has been confirmed. If one scalar field in nature has multiple vacua, there may be others. And inflation magnifies the consequences of these possibilities across enormous scales. The idea of multiple vacua leads naturally to the concept of a cosmic landscape. A landscape where different regions of space-time explore different configurations of physical law. Not a landscape in space, but a landscape of possibilities. Imagine each point in this landscape representing a stable set of laws. Some points allow universes filled with stars and galaxies. Others allow only diffuse radiation. Others collapse quickly. Others expand too fast for structure to form. Inflation could scatter different regions into different points on this landscape, like seeds carried by a quiet wind, each landing in a different valley. Our universe would be one valley among many, one stable configuration in a vast array of possibilities. Physicists explore this landscape not through imagination, but through equations that arise in high-energy physics, quantum field theory, and string theory. The landscape is not a proven structure, but it is a mathematically consistent one, a possibility that emerges naturally when theories are extended to their full depth. As you rest with these ideas, another concept slowly becomes important: the size of the cosmos. Not just the observable universe, but the full extent of space. Even if inflation occurred only once and ended everywhere at the same time, the cosmos could still be enormous. Far larger than anything we can observe. Large enough that random fluctuations would create regions with vastly different properties. If the cosmos extends trillions of times beyond our observable horizon, or quadrillions, or extends without limit, then the number of independent regions becomes effectively infinite. And in an infinite cosmos, even extremely rare conditions will occur somewhere. A region like ours, where conditions allow the formation of complex structures, would simply be one location in a vast ocean of variation. This idea does not require exotic new physics. It follows from the simple possibility that space is much larger than what we can see. The observable universe is not the whole universe. It is only the part from which light has reached us, a small window into a much larger expanse. Another scientific motivation lies in entropy. Entropy describes the number of ways a system can be arranged. Low entropy states are rare, but not impossible. If the universe is large enough, low entropy patches become statistically inevitable. Our observable universe began in a remarkably low entropy state. This allowed matter to clump into galaxies, stars, planets, and life. But low entropy is unusual. If the cosmos contains many regions, most will begin in high entropy states and remain featureless. Only a few rare regions will develop complex structure. We live in one of those rare regions. This does not require design or fine-tuning or hidden purpose. It follows from statistical reasoning applied to a sufficiently large cosmos. A multiverse of regions, many high entropy, a few low entropy, becomes a quiet explanation for why our universe appears so ordered. The next related idea involves cosmic variance. Cosmic variance describes the fact that different regions of the universe may have different statistical properties simply because they sample different parts of the underlying distribution. On small scales, this manifests as differences in galaxy distribution from one region of the sky to another. On larger scales, it could mean differences in the structure of space-time itself. If the cosmos is vast enough, some regions will naturally deviate from the average. The laws of physics may be the same, but their initial conditions differ, and those differences grow over time. One region might form more massive clusters, another might form mostly small galaxies, another might remain mostly empty. These variations become more pronounced across greater distances. And if the cosmos extends far enough, the variation becomes so extreme that distant regions effectively become different universes. Not because the laws changed, but because the initial conditions did. This is a quiet, analytical way in which the multiverse emerges from ordinary cosmology. As we reach the later parts of this section, the scientific motivations for the multiverse align with increasing clarity. Each idea, quantum fluctuations, inflation, vacuum structure, entropy, cosmic variance, expansion, points in a similar direction. The cosmos may be much larger than the part we observe. Different regions may be permanently isolated. Initial conditions may vary across an enormous expanse. Physical laws may take different forms in different vacua. Inflation may create multiple domains. Expansion may create permanent separation. A multiverse becomes not a leap, but a consequence. A gentle conclusion emerges. If our theories accurately describe the early universe, then multiple universes are not only possible, they are a natural outcome. And as this section slowly comes to an end, you can rest with the quiet realization that the scientific basis for the multiverse is broad, layered, and deeply interconnected. Nothing here requires fantasy. Nothing requires abandoning established physics. Each concept draws from well-tested theories. General relativity describes how space-time expands. Quantum mechanics describes how fields fluctuate. Thermodynamics describes statistical behavior. High-energy physics describes vacuum structure. Cosmology describes the horizon of observation. Together, these ideas paint a picture of a cosmos larger than one universe. A cosmos where multiple regions form naturally. A cosmos where isolation is built into the structure of space-time. A cosmos where possibilities extend gently beyond our horizon, and with this slow understanding, you drift forward, ready to explore how the very fabric of quantum mechanics suggests its own kind of multiplicity. As you drift further into the scientific foundation of the multiverse, the ideas become softer, more interconnected, and more revealing of the quiet structure beneath modern cosmology. The goal is never to overwhelm, but to let the science unfold gently, allowing each concept to settle, like slow waves moving across a calm ocean. One of the deepest ideas connecting many threads of thought is the structure of space-time itself. Space-time is not a neutral stage. It is dynamic, responsive, shaped by energy and matter, and capable of expanding without limit. In this expansion lies one of the subtlest reasons physicists consider the possibility of many universes. When space expands faster than light can travel, distant regions become completely inaccessible, not temporarily, but permanently. Even if we waited for trillions of years, light from those regions would never reach us. They are, for all practical purposes, separate universes. If expansion continues indefinitely, the number of such regions increases without bound. Each region has its own cosmic horizon. Each region evolves independently. Each region becomes a self-contained domain. This alone does not prove the multiverse, but it provides the structural framework in which multiple universes can naturally arise. And inflation takes this framework and amplifies it beyond anything we experience in normal cosmology. Inflation is not simply an idea of rapid expansion. It is an idea of exponential expansion, so fast that something the size of a proton could stretch to cosmic dimensions in an instant. And this expansion does not require uniformity. Quantum fields fluctuate, and these fluctuations affect the rate at which inflation ends in different regions. A slight fluctuation, a difference so small that no experiment could ever detect it, can cause one patch of space to exit inflation while its neighbors continue to inflate. These tiny differences are magnified into vast cosmic regions. Each region emerges from inflation with slightly different properties. Each becomes its own universe. The process is quiet, mathematically precise, and consistent with the behavior of quantum fields. What appears dramatic is, in fact, the natural consequence of combining inflation with quantum mechanics. A calm image forms, a vast inflating sea with bubbles of space-time forming gently within it, each bubble drifting out of contact with the others. These bubbles are the pocket universes predicted by inflationary models. But the scientific motivations extend further into the behavior of fields and symmetry. Symmetry is a crucial concept in physics. It determines how forces behave, how particles interact, and how the universe evolves. When symmetries break, when conditions cause the laws of physics to shift into new configurations, the results can vary across space. During periods of extreme energy, such as the era of inflation, fields can settle into different stable states. Each stable state corresponds to a different configuration of physical law. Some configurations lead to universes filled with matter. Others lead to universes that expand too fast for galaxies to form. Others produce universes that collapse quickly. This diversity of possibilities is not hypothetical. It arises from equations that describe how fields behave in high-energy environments. Inflation provides the mechanism to separate these different configurations into different regions. Quantum fluctuations select different outcomes. Expansion isolates them forever. The result is a multiverse emerging from symmetry breaking. Another quiet motivation lies in the idea of vacuum energy. The vacuum is not empty. It holds energy, the energy of fields, and the vacuum may not have a single state. It may have multiple minima, multiple levels of stability. Each minimum represents a universe with its own laws. Some vacua might allow stars, some might not. Some might allow stable atoms, some might not. Some might have 3 dimensions of space, some might have more. This concept is especially important in theories involving extra dimensions and high-energy unification. In these theories, the number of possible vacua is not small. It is enormous, perhaps even unimaginably large. A landscape of vacua appears. And inflation can populate that landscape with universes. This is the scientific basis for the cosmic landscape. It is not a poetic metaphor. It is a mathematical structure, a possibility arising from deep theories of fields and geometry. And as with all other ideas in this section, you do not need to grasp the technical details. Only the shape of the concept matters. A landscape of stable physical laws, inflation scattering universes across it. A different line of reasoning emerges from entropy, the measure of disorder in a system. The early universe, our early universe, was extraordinarily low in entropy. This low entropy allowed matter to clump, forming galaxies, stars, planets, and eventually life. But low entropy states are rare, very rare. In a single universe, it would be surprising to begin in such an ordered condition. But in a multiverse, where countless regions begin with countless initial states, it becomes statistically reasonable that some regions, just a few, will begin with conditions that allow complexity. We live in one of those rare pockets of low entropy. This is not a claim of certainty. It is simply a quiet application of thermodynamics across a large cosmos. Entropy does not need to be tuned by hand. It only needs enough space to explore possibilities. The multiverse provides that space. Another perspective arises from cosmic variance, the understanding that different regions of the universe sample the underlying distribution of matter and energy differently. On small scales, this leads to subtle variations in galaxy clusters. On large scales, it leads to differences in the curvature and density of space-time itself. If the cosmos is vast, cosmic variance becomes extreme. Regions separated by unimaginable distances might have histories so different that they behave as if they are entirely separate universes. Even if the physical laws remain the same, the initial conditions differ, and those differences grow with time. Some regions become rich in structure, others remain sparse, others may even become empty voids with almost no galaxies at all. The multiverse emerges not only from varying laws, but from varying initial conditions. This is the calm analytical thread that runs through much of cosmology. As this section approaches its natural end, the patterns unifying all of these ideas become clear. The multiverse is not a single model, it is a convergence, a meeting point of many independent lines of reasoning. Inflation separates regions. Quantum fields fluctuate, vacua multiply, entropy selects rare pockets, cosmic expansion isolates domains, cosmic variance diversifies outcomes. These ideas do not force a multiverse, but they point strongly toward one. They make a cosmos with multiple universes more natural than a cosmos with only one. A single universe with finely tuned laws and initial conditions would be the exception, not the rule. A multiverse is the quiet, analytical possibility that brings these observations together. And with this gentle understanding, Section 1 concludes. As your mind rests with this foundation, a deeper layer of multiplicity begins to emerge. Not from the large-scale structure of space-time, but from the smallest scales of all, the quantum world. a world where possibilities coexist, a world where probabilities do not collapse until interactions force them apart, a world where the structure of reality might contain far more than the single path we observe. And so you drift into the next section, where quantum mechanics quietly introduces its own kind of multiverse. Quantum mechanics introduces a different kind of multiplicity, one that does not rely on distant regions of space or vast cosmic expansion or different vacuum states. Instead, it arises from the quiet, intricate structure of the microscopic world, a world where certainty dissolves into probabilities, where outcomes remain open until interactions occur, and where the notion of a single unfolding history becomes less obvious than it seems. At the heart of quantum mechanics is the wave function. The wave function does not describe a particle in a single place or a single state, but a spread of possibilities, a gentle distribution of where the particle could be, how it could move, which path it might take. Before a measurement, these possibilities coexist. They are not guesses or approximations, but the actual physical description of the system. A particle is not in one place, but in many potential places. An electron does not have one spin, but a superposition of spins. The world at this scale becomes soft, uncertain, and fundamentally probabilistic. Yet the mathematics is precise. The wave function evolves smoothly, following the Schrödinger equation. Possibilities flow into one another, blend, separate, and recombine, like quiet currents within a larger river of potential. This picture is analytical, rooted in equations, tested by experiment. But it leads to an intriguing idea, one that challenges the classical notion of a single universe. When a quantum system interacts with its environment, something subtle happens. The different possibilities described by the wave function begin to separate, not violently, not abruptly, but gently, as the system becomes entangled with the world around it. Entanglement connects the states of two systems so deeply that the state of one cannot be described independently of the other. As more and more particles interact, the web of entanglement grows. The environment, air molecules, photons, vibrations, collects information about the system. This spreading of information is called decoherence. Decoherence suppresses interference between the different branches of the wave function. The branches stop overlapping, stop interacting, and begin to evolve independently. To an observer inside one branch, it appears as if a single outcome has occurred. But the mathematics tells a different story. All branches continue, all outcomes unfold. The many worlds interpretation emerges from this observation. It does not add anything to quantum mechanics. It simply takes the equations seriously, accepting that if the wave function contains many outcomes, then those outcomes all exist. This does not mean violent splitting or universes popping into existence. It means that the universal wave function contains multiple streams of history, streams that once overlapped but slowly drift apart, becoming separate due to decoherence. Imagine a river branching gently into smaller channels. At first, the water in each branch is still connected, but as the channels diverge, they become independent streams. Quantum branching is like that, a smooth, continuous evolution of the wave function, separating into outcomes that no longer interact. A photon taking two paths around an interferometer, an electron with two possible spins, an atom decaying at one moment or at another, a neuron firing or remaining silent. Each possibility becomes a branch. Each branch contains a version of events consistent with that outcome. This is not speculation. It is an interpretation that follows directly from the linearity of quantum mechanics. In everyday life, these quantum branches are invisible. Decoherence occurs incredibly fast. The environment interacts with systems constantly, turning superpositions into effective classical outcomes in fractions of a second. A dust particle interacting with air molecules decoheres almost instantly. A small object interacting with photons of light decoheres even faster. Macroscopic objects, tables, chairs, planets, are entangled with the environment to such an extent that their wave functions branch continuously. The world we perceive is one branch of this larger wave function, a branch selected not by collapse but by decoherence. The many worlds interpretation says all branches exist. We experience one. A calming realization follows. Quantum branching is not chaotic. It is structured, predictable, governed by precise mathematical rules. The branching is not random. It is determined by how systems interact, how information spreads, and how the wave function evolves. Every branch follows the same physical laws. Every branch emerges from the same underlying structure. Every branch is part of a single, coherent wave function. The multiplicity arises not from creation, but from separation. In this view, the multiverse is not distant. It is not separated by unimaginable stretches of space. It is woven into the behavior of particles everywhere. Every interaction that spreads information, every measurement, every decoherence event contributes to the quiet branching of reality. A photon traveling through two slits takes both paths. A molecule rotating in one direction also rotates in the other. A person making a choice explores multiple outcomes. Each possibility is real within its own branch. Some people imagine this as an infinite explosion of universes, but the mathematics is calmer than that. The wave function simply evolves. It contains many terms. Decoherence ensures that these terms do not interfere. Each term corresponds to a branch of history. The number of branches is vast, but not infinite in a simple sense. It grows with interactions, with entanglement, with time. Yet it grows quietly, not chaotically. The branches do not collide. They do not interact. They unfold alongside one another, like parallel lines that never meet. One of the most powerful demonstrations of these ideas comes from experiments in quantum interference. When particles interfere with themselves, the patterns we observe require the existence of multiple paths. If collapse happened the way some interpretations suggest, the interference would vanish. Instead, the wave function behaves as if all paths exist until decoherence makes them separate. In this way, the many worlds interpretation preserves the continuity of quantum evolution. It removes the need for a special rule for measurement. It allows the equations to operate smoothly at all scales. It also suggests that quantum mechanics contains its own multiverse, a multiverse of branches, a multiverse of outcomes, a multiverse where reality is a vast, evolving tapestry of probabilities crystallizing into separate histories. Yet the interpretation remains gentle. It does not demand belief. It simply offers a way to understand what the mathematics already describes. The branches do not interfere because decoherence suppresses the terms that would cause interference. The branches do not collapse because the wave function never collapses. The branches evolve independently because entanglement locks their histories into separate patterns of information. Analytically, this is a direct consequence of the Schrödinger equation. Philosophically, it is a quiet recognition that reality may be more layered than it appears. Quantum mechanics also introduces another subtle idea, the impossibility of observing other branches. Decoherence ensures that each branch carries its own consistent history. An observer within a branch is entangled with the outcome in that branch. They cannot detect the others, because doing so would require reversing decoherence, a process that would require control over the entire environment. Such control is impossible in practice, not because it is forbidden, but because it requires manipulating every particle that has interacted with the system. The information has spread too widely, too deeply, into too many degrees of freedom. This makes the branches effectively separate. Each branch contains its own observers, its own records, its own unfolding of events. They coexist, but cannot interact. As you drift through these ideas, the concept of a quantum multiverse becomes clearer. It is not a landscape of distant cosmic regions, but a branching structure embedded in the mathematics of quantum theory itself. Every superposition becomes a set of outcomes. Every outcome becomes a branch. Every branch evolves with its own internal consistency. The multiverse becomes not a distant possibility, but a local feature of physics. A quiet multiplicity present in every interaction, every particle, every field. And yet the tone remains gentle. This is not a claim about certainty. It is one interpretation among several, but it is one that aligns smoothly with the equations and one that provides a natural explanation for quantum behavior. A calm understanding emerges. If the many worlds interpretation is correct, then reality contains an immense number of parallel outcomes, not as layers in space, but as branches in the structure of the wave function. And with this realization settling softly, you drift deeper into the quantum world, where entanglement, superposition, and probability continue to unfold. Quantum mechanics continues to offer its quiet, analytical doorway into multiplicity, revealing a structure of reality where outcomes unfold not in isolation, but as parallel threads within a single mathematical framework. As you drift deeper into this landscape, the ideas become clearer, softer, and more coherent, like gentle patterns emerging from a mist. The wave function is central to this picture. It is not merely a tool for prediction, but a complete description of a system's physical state. When the wave function contains multiple possibilities, those possibilities are not placeholders. They are real components of the system's evolution. They move, interact, and interfere. Yet interference is fragile. It requires that the different components of the wave function remain isolated from the environment. Once information about the system spreads, once photons scatter off it, once air molecules collide with it, once vibrations carry its presence into the world, interference disappears. This loss of interference is decoherence. Decoherence does not eliminate the other branches. It merely prevents them from influencing one another. They continue to evolve, but independently, quietly, without crossing. In this way, quantum mechanics naturally describes a branching structure of reality. To understand this branching more deeply, consider a simple quantum experiment. A single photon approaches a beam splitter. In classical terms, the photon must choose a path. But quantum mechanics allows the photon to take both paths simultaneously. The wave function splits into two components, one representing each path. As long as these components can interfere, they remain part of a unified superposition. But if the photon interacts with the environment, if a detector absorbs it, or if information about the path leaks into surrounding particles, the two components decohere. They become separate branches. In one branch, the photon traveled the upper path. In another, it traveled the lower path. Nothing dramatic occurs. There is no explosion of universes. The wave function simply evolves into separate, non-interacting components. Each component becomes a consistent history within its branch. This same process occurs constantly in the world around us. Every interaction between a particle and its environment creates entanglement. And entanglement spreads information. The spread of information destroys interference, and the loss of interference creates branching. The branching is not something we choose. It is not something added to the theory. It is the natural result of quantum evolution. Whenever you observe something, whenever a measurement is made, whenever information is recorded, branching occurs. Your perception, your memory, your awareness becomes part of one branch, not because the others vanish, but because decoherence prevents you from interacting with them. This separation is complete. It cannot be reversed. The information has traveled too far into the environment. To undo it would require controlling every particle involved, a practical impossibility. Thus the branches remain isolated, each containing its own version of events. Some physicists describe this structure as a quantum tree. The trunk represents the shared history before decoherence. The branches represent the divergent outcomes. The branching never stops. Every moment, every interaction, every scattering of light adds more detail to the structure. This picture is not meant to be literal. The branches do not exist in space. They exist in the configuration space of the wave function, a vast abstract space where every possible arrangement of particles is a point, and the wave function assigns amplitude to each point. Within this space, branching is simply the separation of amplitude into components that no longer interfere. It is a quiet, mathematical form of multiplicity. One of the most striking implications of this view is how it preserves the determinism of quantum mechanics. The Schrödinger equation is deterministic. Given a wave function and a Hamiltonian, the evolution is fixed. Yet our everyday experience is filled with randomness. In the many worlds interpretation, this randomness is only apparent. Each outcome occurs in a different branch. The observer perceives one branch, but all branches exist. What appears random is simply the process of becoming entangled with one particular outcome. The mathematics remains continuous and deterministic. The branching creates the illusion of chance. This idea is subtle, but powerful. It aligns with the equations. It removes the need for a special rule for measurement, and it explains why quantum systems behave differently from classical ones. Another aspect of the quantum multiverse arises from entanglement itself. Entanglement is not restricted to pairs of particles. It can involve many particles, entire systems, even entire observers. When two particles become entangled, their properties are linked. If one particle's spin is up and the other's is down, The wave function describes both possibilities, up, down, and down, up. Once decoherence occurs, the two possibilities evolve independently. An observer who measures one particle becomes entangled with the outcome. In one branch, they observe spin up. In another, they observe spin down. The branching is not merely about the system, but about the observer as well. Consciousness does not cause the branching, it participates in it. This is an analytical consequence of treating observers as quantum systems, not as special entities standing outside the laws of physics. As you drift deeper into these ideas, the nature of quantum probability becomes clearer. Probability in the quantum world is not a measure of ignorance. It does not reflect hidden variables or unknown causes. It reflects the distribution of amplitude in the wave function. The wave function assigns weight to different outcomes. These weights determine the relative measure of the branches. In branches with larger amplitude, observers will find themselves experiencing outcomes that appear more likely. In branches with smaller amplitude, observers will experience rarer outcomes. This connection between amplitude and perceived probability is subtle, but it is mathematically consistent. It explains why the Born rule, the rule that probabilities equal amplitude squared, emerges naturally from the structure of the wave function. The many worlds interpretation does not need to add probability by hand. Probability arises from the distribution of amplitude across branches. One might wonder why, if the multiverse of branches is so vast, we do not notice its presence. The answer lies in decoherence. Decoherence separates branches by entangling them with the environment. Once entangled, the branches carry different patterns of information. These patterns become incompatible. To detect another branch, one would need to reverse the entanglement. One would need to erase all records of the interaction. One would need to undo every scattering event, every photon emission, every vibration in the environment. This is not forbidden by physics, but it is practically impossible. The information has diffused too widely. It has become woven into the fabric of the environment. Thus, the branches remain invisible, not because they are hidden, but because the information that distinguishes them is beyond retrieval. This irreversibility gives rise to the classical world we experience. As these ideas settle, the quantum multiverse begins to feel less like an abstract mathematical concept and more like a quiet explanation for the structure of reality. Every interaction becomes a moment of branching. Every superposition becomes a set of outcomes. Every observer becomes part of the structure. This does not diminish the meaning of experience. It simply acknowledges that experience is one thread within a larger tapestry, a tapestry where probabilities become amplitudes, where outcomes become branches, and where reality unfolds along multiple paths simultaneously. As Section 2 gently approaches its midpoint, the essential points become clear. Quantum mechanics naturally describes multiplicity. Decoherence separates outcomes into independent histories. Observers become part of the branching structure. Probability emerges from amplitude, and the multiverse of quantum mechanics is local, woven into every interaction, every particle, every process. With this understanding drifting softly through your thoughts, you move deeper into the quantum world, where the quiet branching of reality continues to unfold. As the quantum picture continues to unfold, the landscape of branching outcomes becomes even more intricate and yet more calming to explore. The goal is not to imagine chaos, but to understand how a single mathematical structure can naturally contain many parallel possibilities, each evolving smoothly, each following the same universal rules. Quantum mechanics does not allow us to speak of a particle having one exact property before measurement. Instead, it allows us to describe a range of potential properties encoded within the wave function. This is not a limitation of knowledge, but a feature of the theory itself. The wave function represents reality before interaction forces one outcome into the foreground. When a quantum system interacts with anything, light, vibration, heat, or an observer, its possibilities separate into branches. The branches do not contradict one another. They simply stop influencing each other. Each becomes its own unfolding timeline, with no mechanism to reconnect. This is why the branching picture feels both mathematically precise and deeply peaceful. Nothing chaotic is required, only the continued flow of interaction, the spreading of information, the quiet work of decoherence. To explore these ideas gently, imagine a simple quantum object, such as an electron. An electron has a property called spin, which can be oriented in different directions. Before measurement, the electron exists in a superposition of spin up and spin down. The wave function contains both possibilities. When an instrument measures the spin, the electron does not choose. The wave function simply separates. In one branch, the observer records spin up. In another, the observer records spin down. The observer, the measuring device, the room around them, all become entangled with the outcome in that branch. Each branch is internally consistent. Each contains its own version of the observer with a memory of one outcome. Both branches are real within the mathematics, but because decoherence prevents them from interacting, each observer perceives only one. The other branch drifts away, not in space, but in configuration space, becoming inaccessible but never erased. This leads to an important realization. Quantum branching includes not just microscopic outcomes, but macroscopic events as well. Everything that depends on microscopic outcomes, thoughts, decisions, behaviors, becomes part of the branching structure. If a neuron fires in one branch and does not fire in another, the consequences ripple outward. A thought forms in one branch and not in another. An action is taken in one branch and not in another. These differences are subtle at first, but they grow as time unfolds. Two branches containing similar observers slowly evolve into vastly different histories. This is not a dramatic multiplication. It is the gentle divergence of possibilities, driven by the same quantum principles that govern the smallest particles. Another layer of understanding comes from recognizing that the wave function describes the entire universe at once, not a single particle or a single experiment, but all particles, all interactions, all systems combined. From this perspective, the universal wave function contains all branches. Every quantum event contributes to its structure. Every interaction defines its shape. Reality is the evolution of this wave function through time. When people speak of the quantum multiverse, they are referring to the different components of this universal wave function. Each component represents a different arrangement of particles, a different sequence of events, a different history. The multiverse, in this sense, is not a collection of separate realities floating in space. It is a single, unified mathematical object containing many internal pathways. This picture is quiet, not dramatic. It suggests that the complexity of existence arises from simple principles, repeated everywhere, all the time. One question that often arises is whether these branches are equally real. From the perspective of the equations, they are. No branch is privileged. None is more fundamental than another. All outcomes follow from the same deterministic evolution. What distinguishes the branches is their amplitude. Some branches have larger amplitude, meaning they contain outcomes that are more likely. Other branches have smaller amplitude, representing rarer outcomes. But amplitude does not determine reality. It determines how frequently observers find themselves in particular branches. This is why the Born rule, probability equals amplitude squared, emerges naturally. It describes the distribution of observer experiences across branches. This connection between amplitude and experience is subtle. It requires no philosophical leap. It arises from the structure of the wave function and the way observers become entangled with outcomes. To visualize this intuitively, imagine standing at a quiet river delta. The river flows smoothly before splitting into two branches. One branch carries most of the water. The other carries only a small stream. Both are real. Both exist. But if you were floating on the water, you would almost certainly find yourself on the larger branch. Quantum mechanics behaves similarly. The branches with larger amplitude contain a greater measure of possible observer experiences. Observers naturally find themselves in those branches, not because the others do not exist, but because amplitude determines the flow of probability. This analogy is not perfect, but it conveys the feeling of how quantum probability emerges from branching. Another important aspect of quantum branching involves reversibility. In principle, the Schrödinger equation is reversible. If one had complete control over every particle, every interaction, every microscopic degree of freedom, one could reverse time and restore interference between branches. But in practice, this is impossible. Decoherence spreads information into the environment so rapidly and so thoroughly that reversing it would require controlling the motion of trillions upon trillions of particles. A single photon scattering off a dust particle creates entanglement with hundreds of millions of atoms. A simple vibration travels through entire systems. Heat leaves imprints in the environment that cannot be undone. This practical irreversibility ensures that the branches remain separate. They cannot interfere. They cannot merge. They evolve independently, forever diverging. This is why the classical world appears stable. It is not a mystery. It is the natural consequence of decoherence in a universe filled with interactions. At this stage, quantum mechanics paints a picture of reality that is far more layered than intuition suggests. Instead of a single path, reality contains many paths. Instead of a single outcome, reality contains many outcomes. Instead of a single world, reality contains many worlds. These worlds are not mystical. They are not speculative. They arise from the precise, tested mathematical structure of quantum theory. Quantum branching does not require exotic assumptions. It only requires accepting that the wave function is real and that its evolution applies universally. The result is a multiverse that exists not beyond the observable cosmos, but within the fabric of every interaction. This understanding provides a gentle transition into the next major ideas. Once the nature of quantum branching becomes clear, another layer of multiplicity emerges. A layer not from quantum probabilities, but from the fundamental constants and laws that shape entire universes. Why do the laws of physics have the values they do? Could they have been different? And if they were different, would universes like ours still form? These questions lead naturally to the cosmic landscape, a vast space of possible laws, where each region corresponds to a different universe, and where the multiverse takes on an even broader form. As you drift even deeper into the quantum landscape, the idea of branching becomes more than a theoretical structure. It becomes a quiet, continuous process woven into the fabric of every interaction in the universe. A process so gentle and so natural that it never disrupts the flow of experience, even though it constantly shapes the underlying structure of reality. The many worlds interpretation does not ask you to imagine abrupt jumps or sudden eruptions of new worlds. Instead, it invites you to imagine the wave function as a smooth river flowing through an unimaginably rich space of possibilities. Whenever a quantum event occurs, the river divides, not with violence, but with softness. One stream becomes two, then two become four, four become eight, and the branching continues, guided by the equations, shaped by decoherence, unfolding with quiet mathematical precision. The river never ends. The branching never pauses. The wave function never collapses. It only evolves. One of the most profound implications of this picture is that reality at the quantum level is not composed of definite states, but of relationships. The wave function encodes how particles relate to each other, how their potentials connect, how their possibilities align. These relationships are delicate. A tiny shift can change the pattern of interference. A slight interaction can create new entanglement. Each interaction nudges the wave function into new shapes, new branches, new configurations. This is why quantum mechanics feels both mysterious and precise. It is not describing things, but patterns. Not fixed outcomes, but evolving relationships. And when those relationships become entangled with the environment, the patterns separate into distinct histories. Each history becomes a branch. Each branch becomes a world. Not a world in space, but a world in the mathematical structure of reality. To understand how universal this process is, imagine a simple scenario. You flip a coin. In classical physics, the coin lands on heads or tails depending on the exact motion of your hand, the air resistance, the details of the impact. But at the deepest level, the atoms in the coin are governed by quantum mechanics. Their interactions are full of superpositions, entanglements, and branching. When you flip the coin, the wave function of the coin, the air, your hand, and your brain becomes entangled. Decoherence separates this enormous web into branches. In one branch, the coin lands on heads. In another, it lands on tails. You, the observer, become part of each branch. In each branch, you have a memory of one outcome. Both outcomes exist, each in its own decohered history. This is not because consciousness creates branches. It is because consciousness is part of the physical system, entangled with the outcome like everything else. The branching is universal. It includes everything, even you. Another key idea is that branching does not require human observation. Quantum mechanics does not distinguish between an observer and a system. A rock, a photon, an air molecule, all can act as observers in the quantum sense. All can become entangled with a system. All can carry information. This removes the need for a special role for consciousness. It keeps the theory strictly physical, strictly mathematical, and consistent with experiments. An air molecule bouncing off a dust particle can create branching. A photon scattering off a leaf can create branching. A vibration traveling through a crystal can create branching. The universe is constantly decohering, constantly differentiating, constantly unfolding into many parallel possibilities. And yet, to any observer within a single branch, the world feels smooth, continuous, singular. This is the quiet beauty of decoherence. As you settle deeper into this idea, the connection between branching and probability becomes clearer. In classical probability, uncertainty reflects ignorance. You might not know whether a coin is heads or tails, but the coin itself is in a definite state. In quantum mechanics, uncertainty is not ignorance. It is genuine multiplicity. Before decoherence, the wave function contains multiple possibilities at once. Probability describes how amplitude flows into different branches, not which branch is real. All branches are real. Probability tells you how often observers find themselves in each branch. This is why the Born rule emerges naturally. Branches with larger amplitude contain proportionally more observer moments. Observers within those branches experience outcomes that match the statistical predictions of quantum theory. It is not that rare branches do not exist. It is that observers are less likely to be in them. With this understanding, quantum mechanics begins to feel less like a theory of randomness and more like a theory of structure. The apparent randomness of quantum events is simply the process of becoming entangled with one branch. The deeper order lies in the wave function itself, which evolves deterministically, smoothly, without exception. This picture brings a quiet order to the seeming chaos of quantum behavior. The wave function guides reality. Decoherence shapes the branches. Entanglement distributes information, and observers find themselves within the branches that match their experiences. It is not mystical. It is not speculative. It is the direct consequence of taking the mathematics seriously. At this point, the quantum multiverse feels tangible, not in the sense of being visible, but in the sense of being conceptually coherent. It explains why the microscopic world behaves so differently from the macroscopic one. It explains why probabilities work the way they do. It explains why decoherence creates classicality. And yet, this quantum multiverse is only one layer of the larger story. It describes a multiplicity of outcomes, but not a multiplicity of laws. It describes branching within a single universal wave function, but not the diverse possibilities of different physical constants, different dimensions, different fundamental structures. To explore that broader landscape, you drift gently into the next section, a section where the multiverse expands beyond quantum mechanics into the realm of high-energy physics, string theory, and the cosmic landscape of possible universes. A landscape where gravity, particles, and even space-time itself may vary, and where the diversity of universes becomes far greater than anything quantum mechanics describes alone. In the vast landscape of scientific thought, there is a gentle shift that occurs when you move from the quantum realm into the realm of high-energy physics. In quantum mechanics, the multiverse arises from branching outcomes, subtle divergences woven into the fabric of probability. But in high-energy physics, in the study of fields, forces, and the deep structure of space-time, the multiverse appears in an entirely different way. Here, the multiplicity does not come from branching histories, but from the possibility that the laws of physics themselves might be different in different regions of existence. Not different outcomes, different laws, a different strength of gravity, a different mass for the electron, a different number of spatial dimensions, a different vacuum state underlying everything. In this section, you drift into that broader landscape, a place where physical law itself becomes a variable, and where the number of possible universes expands far beyond anything quantum mechanics describes alone. To begin softly, imagine the universe as a kind of field-theoretic structure. In modern physics, every force and every particle arises from fields that fill all of space. The electromagnetic field, the gravitational field, the Higgs field, all exist everywhere, even when they seem empty. These fields can take on different configurations. In simple systems, like magnets or crystals, fields settle into particular patterns depending on temperature or pressure. In deeper theories, the same thing can occur at cosmic scales. A field may have multiple stable states, each corresponding to a different version of physical law. These states are called vacua. A vacuum is not empty space, it is a configuration of fields, and different vacua lead to different universes. One vacuum might produce strong gravity, another might produce weak gravity, one might produce stable atoms, another might produce no atoms at all. In this picture, the multiverse emerges from the landscape of possible vacuum states. This landscape becomes most vivid in string theory, a framework that attempts to unify quantum mechanics and gravity. In string theory, the fundamental objects are not particles, but tiny vibrating loops or strings. The way a string vibrates determines what particle it becomes: an electron, a quark, a photon, a graviton. But strings cannot vibrate freely. Their possible vibration states depend on the shape of extraspatial dimensions. String theory naturally predicts more than 3 spatial dimensions. Some versions predict 6 additional dimensions, others predict 7. These extra dimensions are not visible because they are compactified, curled up into small shapes far beyond everyday perception. But these shapes can vary. Just as a musical instrument produces different sounds depending on its shape, the extra dimensions in string theory produce different laws of physics depending on their geometry. A slightly different twist of an extra dimension can change the mass of a particle. A slightly different curvature can alter the strength of a force. A slightly different size can make a universe lifeless, or unable to form stars, or radically different in ways that defy intuition. This is why physicists speak of the string theory landscape, a vast collection of possible vacuum states, each corresponding to a different universe with different properties. Some estimates suggest there may be 10 to the power of 500 possible vacua, a number so large it dwarfs the number of atoms in the observable universe. Why would nature contain so many possible vacua? The answer lies in how compactification works. The extra dimensions can fold, twist, and stabilize in countless ways. Each unique configuration leads to a different low-energy world. In one vacuum, the electron may be stable. In another, there may be no electrons. In another, nuclear forces may bind far more tightly. In another, stars may never form. These possibilities are not imaginary. They arise from the mathematical structure of the theory. Whether string theory is correct or not, the concept it introduces is profound. The laws of physics may not be unique. They may be one choice among many, selected not by necessity, but by the vacuum state our region of space-time occupies. This leads to a quiet but powerful question. Why does our universe have the laws it does? Why is gravity so weak compared to electromagnetism? Why do particles have the masses they have? Why is the cosmological constant so small, but not zero? Why do the fundamental constants appear finely tuned for the existence of stars, planets, and life? In the traditional view, these constants were simply accepted. They were the numbers nature provided. But in the landscape view, these constants may vary across different vacua. Different universes may exist with different constants. Ours is simply one where the constants happen to allow complexity. This is not an argument from imagination. It arises from the structure of field theory. Different minima of a potential correspond to different physical laws. Inflation can populate these minima. Quantum fluctuations can push regions of space into different vacua. Each region becomes a universe with its own parameters. The multiverse arises naturally from the structure of potential energy in high-dimensional field theories. To understand this more gently, imagine a landscape of hills and valleys. Each valley represents a stable vacuum state. A field rolls down the landscape and settles into one valley. But if inflation stretches space while the field is still rolling, different regions can settle into different valleys. Each valley is a universe. Each universe has different physics. The landscape contains them all. Some valleys produce universes that expand too quickly. Some produce universes that collapse immediately. Some produce universes with no atoms. Some produce universes rich with chemistry, stars, planets, and complexity. Our universe occupies one such valley. Nothing demands that it be the only valley. Nothing demands that it be the deepest, the simplest, or the most natural. It is simply one option. Another way universes may differ involves symmetry breaking. In high-energy physics, forces that appear distinct at low energies, electromagnetism, gravity, the nuclear forces, may unify at extremely high energies. As the universe cools, these unified forces break into separate forms. The way symmetry breaks can differ across regions. Different symmetry breaking leads to different physical laws. This is analogous to how water freezes. When water becomes ice, its symmetry breaks. The molecules arrange themselves into a crystal structure. But the orientation of the crystal can vary from region to region. Each region becomes a domain with different properties. In cosmology, similar domain structures can arise from symmetry breaking. These domains may never come into contact because of inflation. Each domain is, for all practical purposes, a separate universe. This is another path to a multiverse. At this stage, it becomes clear that the cosmic landscape is not a single idea, but a convergence of many ideas. Vacua that differ in energy, extra dimensions that differ in shape, forces that break in different ways. Fields that stabilize into different configurations. Each configuration produces a universe with its own laws. Some universes may look like ours, some may be wildly different, some may allow no structure at all. This diversity is not philosophical. It is the natural consequence of combining field theory, symmetry, and high-dimensional geometry. The multiverse emerges not from speculation, but from the flexibility inherent in physical law. With this understanding forming gently in your mind, the landscape becomes a kind of cosmic garden, a place filled with countless potential universes, each a different blossom of physics. Some blossoms flourish, some fail, some never open, some expand into grand cosmic structures. And yet, amid this diversity, one question rises softly. Why does our universe appear so finely tuned for complexity? Why do the constants fall within narrow ranges? Why do the laws allow stable atoms, long-lived stars, and chemistry? The anthropic principle offers a calm answer, not a dramatic or mystical one, simply the idea that observers can only exist in universes where conditions allow observers. Most universes may be sterile, most may be dark, most may be brief flashes of unstable physics. But in a landscape with vast possibilities, even rare conditions occur somewhere. We happen to be in one of the rare places where complexity thrives. As this section nears its close, the key idea becomes clear. The multiverse of the cosmic landscape is not built from branching histories, but from diverse configurations of physical law. It is a space of possibilities, not outcomes, a realm where universes differ not in events, but in the fundamental rules that govern them. And with this understanding, you drift gently toward the next chapter, where infinity itself becomes a source of multiplicity, and where the repetition of patterns across boundless space introduces an entirely different kind of multiverse. In the landscape of possible universes, the differences between physical laws unfold quietly, as if nature were exploring every configuration it can support. Imagine a field with many valleys, each valley representing a stable form of physics, each one shaped by different values of the constants we take for granted. Gravity could be stronger or weaker, light could travel at a different speed, particles could have different masses, or might not exist at all. In some universes, the forces might unify in elegant ways, forming smooth interactions that bind matter together with ease. In others, the forces might never separate cleanly, leaving a cosmos where structure never takes shape. The idea that these constants can vary does not come from imagination alone. It arises naturally from theories that try to unify particles and forces under a single framework. String theory, for example, describes the fundamental constituents of nature not as points, but as tiny vibrating strings. The way these strings vibrate determines the particles and forces we observe, and those vibrations depend on the geometry of dimensions we cannot see. If the extra dimensions are curled tightly in one shape, the constants take one set of values. If they curl in a different shape, an entirely different set emerges. In this way, the geometry of hidden dimensions becomes the blueprint for a universe. And because there are so many possible geometric shapes, the number of possible blueprints becomes enormous, far beyond anything we could hope to count. This vast collection of possible solutions is called the cosmic landscape, a terrain of countless vacuum states. each one representing a different universe with its own rules. Most of these regions would not support stars or planets or chemistry. Many would collapse immediately. Others would expand so quickly that nothing could form within them. But a small subset, perhaps an extremely small subset, would allow complexity to arise. The universe we inhabit seems to belong to that rare category. This raises a gentle but important question. Why do the constants in our universe fall into the narrow range that allows structure to exist? This is where the anthropic principle sometimes enters the discussion. Not as a final answer, but as a quiet reminder. If many universes exist with many different physical laws, then observers will naturally find themselves in universes that allow observers to exist. It sounds trivial, but it becomes meaningful when we consider how sensitive the universe is to small changes. If gravity were slightly stronger, stars would burn out too quickly. If the cosmological constant were slightly larger, galaxies would never form. If the electron's mass differed by a small amount, atoms might not be stable. Out of the vast landscape of possibilities, complexity seems to emerge only in narrow pockets, like oases in a broad desert of barren universes. The landscape picture does not claim we know how many such pockets exist, nor does it claim to know how common life might be within them. It simply highlights that the conditions we observe may be part of a broader pattern, one in which universes naturally explore many configurations. Quantum field theory supports a similar view. Fields can settle into many different stable states, and each state can produce different forms of physics. Inflation can stretch each stable region into a separate universe, making diversity not only possible, but almost inevitable. And if the cosmos is exploring this landscape continuously, then new universes might be forming even now, far beyond our horizon, drifting in the vastness, with laws we could not imagine. Some might have more dimensions than ours. Some might have fewer. Some might lack electromagnetism, or contain forces we have never encountered. This is not speculation in the casual sense, but a natural extension of equations that already describe the particles and forces we observe. When physicists speak of a landscape, they often describe it as a terrain dotted with valleys, hills, and plateaus. The deeper the valley, the more stable the corresponding universe. Our universe sits in one such valley, stable enough to endure for billions of years, calm enough to allow galaxies to form, gentle enough to allow life to arise. But the landscape contains many valleys, each one a potential universe. Some valleys lie close to one another, separated only by small ridges. Transitions between them could occur under extreme conditions, though such transitions would not be gentle. They would reshape the vacuum itself, creating a new universe with new laws. In the early moments of cosmic inflation, vast regions of space might have tumbled into different valleys, locking in the constants for those regions. Over time, inflation would stretch each region apart, isolating them, making each one effectively its own universe, unreachable from the others. As we drift further into this idea, the landscape becomes not a metaphor, but a practical tool. It allows physicists to understand why certain combinations of constants appear natural, while others seem impossible. It also provides a quiet explanation for why our universe appears finely tuned. If many universes exist, some will naturally fall within the narrow band that supports complex structures. This does not diminish the specialness of our universe. It simply places that specialness within a broader context. The landscape does not offer certainty. It offers possibility, and possibility is often more calming than certainty, because it allows the mind to drift, exploring gently, without the pressure of arriving at an answer. As we move through these ideas, the landscape becomes a soft backdrop, a reminder that our universe could be part of a much larger pattern, woven from geometry, fields, and quiet mathematical structure. In the next ideas we explore, we drift beyond the landscape into thoughts of infinity, and the surprising consequences of a space that never ends. In the quiet vastness of thought, the idea of a cosmic landscape settles like a gentle mist over the mind. You can imagine reality not as a single fixed universe, but as one point in a wide field of possibilities. In this field, the laws of physics are not rigid commands, they are outcomes, delicate results of deeper structures, shaped by the way fields settle, by the way hidden dimensions curl, by the way the vacuum of space chooses a particular state. The universe you know, with its familiar constants and particles, is one such outcome. But the mathematics that underlies modern physics suggests that there may be many others. To move deeper into this, begin again with the idea of a vacuum. In everyday language, a vacuum is empty space, a simple absence of matter. In high-energy physics, a vacuum is something richer. It is the lowest energy configuration of all the fields that fill space. A stable arrangement of values that every point in space shares. If you change the vacuum, you change the behavior of those fields. And if you change the behavior of the fields, you change the laws of physics. The charge of particles, the strength of forces, the nature of interactions, all flow quietly from the vacuum state. Our universe lives in one such state, but the equations suggest that there could be many stable states, many possible vacua, each one corresponding to a different universe in the landscape. Imagine a smooth surface with many valleys, some shallow, some deep, some narrow and sharp, others broad and gentle. This surface is a picture of a potential energy function. A field placed on this surface will roll down and settle into one of the valleys. The valley it chooses determines the vacuum, and the vacuum determines the physics. In the early universe, when energies were extremely high, fields may not yet have settled into a single valley. They may have fluctuated, climbing over ridges, lingering on plateaus. While cosmic inflation stretched space, different regions could have dropped into different valleys, each region becoming a separate universe, with its own vacuum, its own constants, its own long-term behavior. This is one way the cosmic landscape can turn mathematical possibility into a multiverse of actual universes. To feel the delicacy of this idea, consider how sensitive our universe is to small changes in its constants. If the strength of gravity were modestly larger, massive stars would collapse more easily, their nuclear fuel burning rapidly, their lifetimes shortened. Heavy elements might still form, but the window for planets and life to develop around long-lived stars would shrink dramatically. If gravity were slightly weaker, matter would struggle to clump. Gas clouds would take far longer to collapse into stars, or might never collapse at all. The universe could remain a diffuse fog with occasional oversized stars that burn out quickly. In both directions, the delicate balance that allows galaxies of long-lived stars would be disrupted. Similarly, if the electromagnetic interaction were a bit stronger, electrons would be held too tightly to nuclei. Chemical bonds would change, molecules would behave differently. Complex chemistry might never arise. If it were a bit weaker, atoms could become fragile, easily disrupted, unable to form stable structures over cosmic time. In this sense, our universe sits in a narrow band of parameter space where complexity is possible. Within the landscape, most vacua may produce universes where this kind of complexity simply never appears. The cosmological constant, the energy density of the vacuum itself, tells a similar story. If the cosmological constant were much larger and positive, space would expand so quickly that matter could never gather into galaxies. Clouds of gas would be pulled apart before gravity could bring them together. The universe would remain thin, featureless. Without stars or planets, if it were significantly negative, gravity would eventually dominate, causing the universe to recollapse in a short cosmic time. Either way, long-lasting structures would not emerge. Only a tiny range around the small positive value we observe allows a universe that expands, yet still forms galaxies. Within a large landscape of possible vacua, most values of the vacuum energy do not permit such worlds. Our universe appears to occupy one of the rare regions where conditions line up. This is where the anthropic perspective offers a calm way to think. It does not claim that the universe exists for the purpose of life. Instead, it simply notes that any observers, any beings capable of asking questions, will necessarily find themselves in regions of the landscape where observers can exist. If there are many universes, each with different laws, you should not be surprised to find yourself in one of the rare universes that allow complexity. It would be impossible to observe a universe that did not. The anthropic principle is thus less a grand explanation and more a quiet filter on perspective. A reminder that when you look out at the cosmos, you are seeing one of the few arrangements that make looking out possible. This idea can feel unsettling at first, because it replaces uniqueness with context. Instead of thinking that the constants of nature must have a single deep reason, you allow for the possibility that they are one choice among many options the landscape provides. But in a sleep-friendly frame, this leads not to anxiety, but to a sense of gentle openness. The universe is no less real, no less beautiful, no less lawful. It is simply part of something even larger, a broader space of potential universes, each resting in its own vacuum, each following its own quietly consistent rules. Another piece of the landscape picture involves transitions between vacua. In some models, a universe can begin in a higher energy vacuum, a state that is stable enough to last for a very long time, but not absolutely stable. Quantum mechanics allows such a vacuum to tunnel to a lower energy state, like a ball that seems stuck in a shallow valley, but occasionally slips through the hill into a deeper one. This is called false vacuum decay. In principle, such a transition would change the vacuum everywhere inside an expanding bubble. The laws of physics inside the bubble would differ from those outside. It is natural to imagine this as dramatic, but from the perspective of physics, it is a smooth process governed by the same equations that describe other quantum events. Whether our universe resides in a true vacuum or a long-lived false vacuum is unknown. If it is long-lived, its lifetime could be vastly greater than the timescales of stars and galaxies, so long that the possibility of decay has no practical effect on anything we will ever see. In this narration, the purpose of such ideas is not to introduce fear, but to show how deeply the landscape extends. Even the vacuum itself may have a history, a before and after, embedded within a greater space of possibilities. Stepping back, the cosmic landscape suggests that our familiar universe is one of many possible ground states of a deeper theory. Each ground state gives rise to its own form of matter, its own interactions, its own cosmic evolution. In many of those states, no complex structures form at all. In a sparse subset, structures emerge. In a smaller subset still, the structures last long enough and behave richly enough to support observers. We inhabit one of those rare regions, not because it was chosen in a special way, but because that is the only kind of region that can contain beings who ask why the constants have the values they do. This view does not answer every question. It does not tell us exactly how many vacua exist, or how they are populated, or what fraction produce structure, but it places our universe within a wider mathematical context, and that alone can be strangely comforting, to know that the laws you see are not the only way reality could be, but one peaceful realization among many. As these thoughts settle, you can imagine the landscape again as a calm field of light. Each point in the field is a universe, faintly glowing with its own parameters. Some lights flicker briefly and fade, some never truly brighten. A few shine steadily for long ages. Among those few, there are universes with galaxies, with stars, with long-lived atoms, with the slow chemistry that eventually wonders about its own existence. Our universe is one such light, one quiet glow in the vast landscape. And as the mind rests on that image, another idea begins to approach softly. If the landscape is large, and if space itself may be infinite, then these lights might not only vary, they might repeat. Patterns like ours, perhaps scattered at unimaginable distances, appearing again and again across an endless expanse. But that is the theme of the next step in this journey. For now, it is enough to float gently above the landscape of laws, feeling how rare and yet how natural our own universe can be, a single, tranquil possibility in a multiverse of many possible worlds. In an infinite cosmos, the mind begins to settle into a strange and gentle truth, that if space stretches without boundary, if it expands not just far beyond our sight, but far beyond anything that light could ever hope to reach, then repetition is not simply possible. It becomes inevitable. This idea rests quietly within modern cosmology, not as a fantasy, but as a mathematical consequence of unbounded space. And so we begin here, in the soft concept of infinity, a space so immense that every possible arrangement of matter, every pattern, every structure, every quiet configuration of particles will occur again and again and again, not because the universe wishes to repeat itself, but because infinity leaves no alternative. When cosmologists speak of infinite space, they do not mean a blank void stretching outward alone. They mean a tapestry so vast that even the most distant galaxy clusters we can observe. Even the faintest smudge of light at the edge of our telescopes would be only the first grain of sand on an endless cosmic shore. And in that endlessness, patterns re-emerge, not as copies made intentionally, but as statistical echoes, born from the sheer combinatorial richness of matter. This is the soft foundation of the idea, a place where mathematics whispers that if you have infinite space and finite ways matter can arrange itself in a region the size of our observable universe, then somewhere, far beyond any reachable horizon, there must exist another region arranged the same way, not close, not accessible, not even meaningful in any practical sense, but real in the quiet way infinity makes things real. This is where the concept of distant doppelgangers arises, not mystical twins, but parallel regions of space where atoms have settled by chance into patterns indistinguishable from ours. A world where a star like our sun glows gently in a familiar sky. A world where a planet shaped like Earth circles it. A world where life might arise in familiar rhythms and where histories unfold so similarly that for a moment one might imagine a version of oneself looking up at their night sky, thinking thoughts not unlike these. But even this imagery, as dreamlike as it may be, is not the scientific core of the idea. The scientific core lies in entropy, combinatorics, and the nature of infinite sets. Imagine a deck of cards shuffled endlessly. If you shuffle long enough, eventually, one day, you will see the same arrangement again, not because the deck remembers, but because infinity does not run out of chances. Now imagine a deck not of 52 cards, but of every particle in a region of space, a number so immense that it defies metaphor. In an infinite universe, that arrangement, unlikely beyond imagining, would still repeat. But repetition does not stop at exactness. It includes near repetitions, worlds that resemble ours but diverge in small ways, worlds where a single molecular event differed, where a single choice branched another way, worlds that are cousins rather than twins. These ideas take shape slowly, drifting through the mind like soft mathematical tides, and so we follow them, gently, into the nature of entropy. Entropy measures the number of ways a system can be arranged while appearing the same from afar. It is why gas molecules fill a room, why stars evolve through predictable stages, why the universe grows more structured in one sense and more disordered in another. If space is infinite, then entropy does not merely rise, it explores every possibility. Regions form with low entropy, high entropy, and everything between, simply because infinite space has room for all of them. In such a cosmos, the familiar emerges by chance, not by design. Stars assemble because gravity permits it. Galaxies swirl because matter finds stable orbits. Life forms because chemistry provides paths that can be explored. And somewhere, far beyond any reachable point, these processes repeat, not because they are destined to repeat, but because infinity is generous. It allows every combination, every configuration, every quiet variation of cosmic structure. Mathematicians describe this gently using the idea of the cosmic patch, the volume of space we can observe, a sphere whose radius is limited by the speed of light and the age of cosmic expansion. Beyond that sphere, there is no edge, only more space, unobservable, unreachable, but governed by the same physics. Each patch contains a finite number of possible arrangements of matter because quantum mechanics discretizes the smallest scales and relativity bounds the largest. And if the number of patches is infinite, then the number of arrangements repeats, not frequently, not nearby, but inevitably. This is the quiet heart of cosmological repetition. Now imagine drifting across these infinite planes of space, floating past superclusters of galaxies that resemble those we know, then beyond them, into regions where the distribution of galaxies differs subtly, where the cosmic web stretches in unfamiliar patterns, and farther still, beyond distances so vast that time itself seems to dissolve, you drift past a region where the arrangement mirrors ours so closely that if one could hold both in their mind at once, the resemblance would be almost perfect. But the great distances ensure these repetitions remain forever inaccessible, forever unconnected, forever isolated by the expansion of space. This isolation is important because it avoids paradox. A duplicate Earth, a duplicate solar system, a duplicate you, existing unimaginably far away, poses no conflict with physics because there is no communication, no influence, no causal overlap. Each region is sealed by distance, separated by horizons that no light can cross. A horizon defines the boundary of what can be observed, a boundary not of matter, but of information. This boundary grows slowly over time, but the universe expands faster, pushing distant regions away, ensuring they remain forever hidden. This is why repetition in an infinite universe is not a threat to identity, not a challenge to personal meaning. It is simply a quiet mathematical truth, one that unfolds gently when infinity and probability meet. As we drift deeper into this idea, we begin to see how thermodynamics ties into it. Entropy increases over time because systems evolve toward the states that are most statistically likely. In an infinite cosmos, even rare states occur infinitely many times. This includes regions of high order, low order, and everything in between. Some cosmologists propose that our observable universe began as a natural fluctuation, a region where entropy was unusually low. Not because of a deeper reason, but because infinity leaves room for even the rarest events. Others argue that inflation created smoothness and uniformity, not by chance, but by physics. Both ideas coexist gently, neither disproving the other, because in an infinite cosmos, both chance and mechanism contribute to structure. The repetition of patterns does not imply intent nor destiny. It is simply the quiet mathematics of infinite sets. As we continue drifting, the mind relaxes into this scale, a scale so large, so peaceful, so unconcerned by the details of any single world, that one feels a soft detachment, a sense of floating through possibilities. Each one a gentle echo of another, each one shaped by laws that do not insist on uniqueness. In this vast landscape of repetition, we can imagine statistical doppelgangers of Earth, regions where circumstances align so closely that histories appear nearly identical. But there would also be worlds where a small difference cascaded into a new path, where galaxies evolved differently, where stars lived shorter lives, where planets formed with unfamiliar chemistries. These variations are just as inevitable as the repetitions. That is the beauty of infinite space. It does not choose outcomes, it allows them. And so we drift further into the quiet realization that infinity softens the importance of any single arrangement. Uniqueness becomes relative, not absolute. Our world is special to us, but in the mathematics of infinity, it is one possibility among countless others. This is not diminishing, it is comforting, because it suggests the cosmos is vast enough to hold every version of peace, every version of warmth, every moment that could ever be imagined, even the quiet moment we are in now. As these ideas settle, we gently transition toward the next theme, not by abrupt shift, but by drifting. Just as space itself drifts outward, carrying galaxies with it, we move from the infinite horizontal scale of repetition into the vertical depth of dimensions. A new question forms softly. If space can be infinite in extent, could it also possess hidden layers, hidden directions the human senses cannot perceive? And if so, could universes exist not beside ours in the vastness of distance, but near us in the stillness of dimensions, invisible, adjacent, yet entirely separate? And with that gentle question, we drift toward the world of higher dimensions and the quiet geometry of brains. The idea that repetition becomes inevitable in an infinite cosmos is not a poetic dream. It is a mathematical consequence of scale. Once the universe grows without limit, once there is no boundary to the expanse of space, then the number of possible arrangements of matter, even though enormous, is still finite compared to the size of that endless stage. This is the quiet paradox that lies at the heart of repetition. A space that has no edge can hold patterns that appear again and again, not because the universe has an intention, but because probability demands it. Imagine a night sky with no end, a canvas so wide that every possible arrangement of stars must appear somewhere, not close by, not in any region we could reach, but far beyond any cosmic horizon, in places so distant that even light, traveling forever, could never bridge the gulf. In such a space, the idea of a doppelganger world is not fiction. It is a statistical whisper carried by the logic of infinity. When cosmologists consider these ideas, they do so with care, not as fantasy, but as an implication of scale that arises when one studies the universe's geometry with precision. If space continues endlessly, and if the laws of physics allow only a certain number of ways for matter and energy to arrange themselves, then patterns must repeat. Not because the universe cycles, and not because anything is mirrored intentionally, but because infinity is large enough to hold duplicates by necessity. The number of different ways the atoms in your body could be arranged is vast beyond comprehension, far greater than any number the mind can comfortably hold, yet still finite. And when a finite number of possibilities is placed inside an infinite space, some of those possibilities must repeat, scattered across unimaginable distances, segmented by horizons that no civilization could ever cross. Even if one traveled forever, riding the deepest currents of space-time, there would still be regions so remote that light emitted from them now will never reach us, not even over eternity. These horizons define the limits of what is observable, but not the limits of what exists. Beyond those boundaries, far beyond the visible sphere, lie regions that follow the same laws of physics, regions that formed stars and galaxies just as ours did, regions shaped by the same cosmic evolution, but with different details, different patterns, and somewhere, the inevitable repetition of familiar ones. A world with a mountain landscape like a memory you have never lived, a world where the arrangement of clouds resembles an image from your childhood, a world where geological accidents played out in similar sequences, producing an Earth-like surface with an ocean in a familiar curve, a peninsula that mirrors a map you know, not because of meaning, but because of sheer combinatorial inevitability. Even more distant, buried in the endless plains of infinite space, there would be worlds where life emerges, if life is permitted by the laws of physics. Whether life is common or rare, its probability, multiplied by infinity, leads to astonishing consequences. Because infinity, multiplied by even the smallest non-zero probability, remains infinite. This is one of the most peaceful and unsettling and mathematically gentle ideas in cosmology. Somewhere, in regions that no signal can ever bridge, there might be a being who looks like you, not metaphorically, but atom for atom identical, simply because the number of possible human configurations, though enormous, fits inside the space of combinatorial repetition. This idea is not presented to disturb, but to clarify the strangeness of an infinite cosmos. It does not imply that identity is shared, or that consciousness is duplicated, or that there is any connection at all between separate regions. It only means that if the universe is infinite, then the combinatorial space of matter permits repetition. These repetitions are not connected to us, not entangled with our existence, not reflections of our choices. They are simply arrangements of particles that occur again, the way patterns appear multiple times in a quilt made from limited fabric, when the quilt stretches without end. To understand why this is taken seriously, one must consider entropy, the measure of how many microstates correspond to a single macroscopic configuration. Even a simple gas in a container has a finite number of microstates, exceedingly large, but countable. A human body has far more microstates, but still a finite number. A planet has yet more, yet still finite. A galaxy contains so much complexity that counting its microstates becomes unimaginable, and still finite. Once finitude meets infinity, repetition ceases to be strange. It becomes inevitable, as quiet and unavoidable as the repeating ripples on an infinite pond. Though the pond may be too large to ever see its farthest reaches, the nature of its surface guarantees repeating waves. In cosmology, this reasoning rests not on speculation, but on the mathematics of infinite sets. And yet, the distances involved are so vast, so deep beyond anything measurable, that these mirrored regions pose no philosophical threat, only a conceptual curiosity. Because they are inaccessible, forever beyond reach, the expansion of the universe accelerates, driven by dark energy, stretching space at a rate that ensures that certain regions recede faster than light can chase them. These regions do not move through space faster than light, but space itself expands between us and them, carrying them over the horizon, beyond observational influence forever. This means that the notion of repeated patterns does not challenge individuality, does not diminish the uniqueness of your experience, does not imply any shared connection. It simply reflects the scale of an infinite cosmos, a cosmos so immensely wide that all configurations must occur not close by, but scattered sparsely across unreachable expanses. There is a calming perspective hidden within this idea, a reminder that infinity does not produce chaos, but structure, repetition, patterns that echo quietly through the cosmos, not as mirrors but as mathematical necessities. And there is comfort in recognizing that these repetitions, though implied by the scale of existence, remain abstract, forever distant, forever separate from the narrative of our world. They exist without influence, without entanglement, as independent outcomes of cosmic probability. In local terms, our observable universe is vast enough on its own, filled with galaxies and voids, clusters and filaments, shaped by gravity's slow sculpting over billions of years. But beyond what we can see, beyond the cosmic light horizon, where no telescope will ever reach, lies an unbounded sea of space, a realm where galaxies formed under similar physical laws, but with different details, different histories, different accidents of stellar birth and collapse. Somewhere in that sea, repetition blossoms quietly. A star identical to our sun might ignite, burning hydrogen with the same luminance, the same temperature, the same spectral signature, not because of destiny, but because the number of possible stars is limited, and the number of places where stars may form is limitless. Farther still, in more remote patches of cosmic infinity, another sun might shine, its planets arranged in familiar ways, its orbital patterns reflecting familiar dynamics, not by design, but by statistics. Whether any such regions exist depends entirely on whether space is infinite. If space is finite, with a closed geometry, or with a topology that restricts its total volume, then repetition might not occur. But if space is truly infinite, as many cosmological models suggest, then the mathematics of repetition emerges naturally, not as fantasy, but as the quiet logic of scale. Infinity is difficult for the mind to hold, so cosmologists describe these ideas gently, framing them not as literal duplicates, but as consequences of combinatorial possibility. Many people imagine these distant regions as copies in some metaphysical sense, but scientists view them as unrelated outcomes, separated by cosmological horizons, bound by no shared story, connected by no mechanism, just quiet repetitions of patterns, the way snowflakes can form similar shapes, even though each is forged independently. This perspective leads to deeper reflections on entropy, because entropy describes the number of ways a system can be arranged, while still appearing the same at large scales. A room filled with air can have trillions upon trillions of microscopic arrangements, yet appear identical to the human eye. The same is true for galaxies, for planets, for biological structures. Entropy defines the count of possible configurations, and when the stage upon which these configurations appear is infinite, repetition follows. This repetition is not ordered, not patterned in regular intervals, not arranged neatly. It appears randomly, scattered across cosmic distances so enormous that even naming them stretches human imagination, distances so wide that numbers fail, leaving only metaphors, oceanic expanses of space-time, silent and unreachable. Across those expanses, repetition whispers quietly, not because the universe is pretending to mirror itself, but because infinity provides enough space for all possibilities. This is one of the softest ideas in cosmology. An idea that sits gently in the mind once understood, an idea that asks for no urgency, no fear, no philosophical burden, just acceptance of scale, acceptance that the universe, if boundless, can hold echoes that we can never hear. And in this acceptance there is peace, a recognition that our place in the cosmos is unique to us, even if the universe is large enough to repeat patterns elsewhere, because distance protects individuality, ensuring that each region lives out its own quiet history, unobserved by all others. This understanding also connects faintly to the structure of large-scale cosmic patterns. Galaxies gather along threads of dark matter, forming filaments that stretch across vast distances, separated by voids that expand quietly as the universe grows. In an infinite cosmos, these filaments continue without end, branching, curving, winding gently through space-time. Some regions might contain structures resembling those near us, spiral galaxies with similar dimensions, clusters shaped by similar gravitational histories, voids carved by similar flows. But these similarities arise from the physics of structure formation, not from any direct repetition, just the quiet echo of the same cosmic rules played out across endless distance. The more deeply one contemplates infinity, the more natural repetition appears, not as magic, but as mathematics. It is a reminder that possibility expands with scale, and that in a universe large enough, everything that can happen might happen somewhere. This does not diminish the beauty of our own world or the uniqueness of our moments, because these repetitions do not touch us and never will. They lie beyond all horizons, as unreachable as the dreams of other worlds. In contemplating these vast distances, a calmness settles in, a sense that the universe is immense enough to hold all possibilities, yet gentle enough to let each region exist in quiet solitude. And as space expands, as galaxies drift farther apart, as horizons widen, this solitude deepens, leaving each cosmic region, each island of galaxies, to write its own story, unaffected by the faint repetitions that occur far beyond its sight. This idea, the idea of repetition in infinity, closes gently around the mind, like a soft blanket, inviting rest, inviting the listener to drift through these possibilities, without fear, without urgency, without the need to grasp every implication, simply resting with the scale of existence. And the quiet hum of probability that flows through an infinite cosmos. And now, the thoughts continue their gentle drift, carrying us deeper into the idea of endless space and the calm that comes from realizing how far it extends. The horizon grows quiet, the stars fade into distance, and the mind settles into the soft recognition that infinity, even in its vastness, is peaceful. A landscape of endless possibility, stretching without edge, without boundary, without end, where repetition arises not from intention, but from the quiet, inevitable mathematics of an infinite night. When cosmologists talk about repetition in an infinite cosmos, they also consider a subtler idea, the possibility that space might be large but not infinite, yet still capable of repeating itself through geometry. In this view, the universe could have a finite volume, but a shape that allows patterns to wrap around, like the surface of a sphere, or the geometry of a torus, where moving in one direction long enough brings you back to where you started. Not because space ends, but because it curves back onto itself, quietly, smoothly, with no boundary. If the universe had such a topology, then distant regions might not be different regions at all, but echoes of the same space, seen along different paths, like reflections in a hall of mirrors, subtle, distant, and stretched by cosmic expansion. This idea is not the mainstream view, but it is taken seriously because general relativity allows many possible global shapes, and observations do not yet rule out every option. A universe with a wraparound geometry would create a different kind of repetition, not caused by infinity, but by the finite looping of space itself. Patterns could repeat because the universe folds gently around itself, allowing light to travel in ways that produce faint, elongated echoes of distant structures. In practice, cosmic expansion makes such echoes difficult to detect, because space stretches faster than light can loop around, but the possibility remains, a geometric whisper at the edges of cosmological thinking. These ideas show that repetition is not limited to the infinite case, but arises from the deeper structure of space-time. Even in finite models, repetition could occur, not from combinatorics, but from curvature. And so the idea of cosmic repetition has two quiet branches, one flowing from infinity, the other from topology. Yet cosmologists discuss these ideas with careful restraint, because repetition is not something we can test directly, not something that instruments can probe, not something that future telescopes will easily reveal. It is a mathematical consequence, not an observable event, a conceptual tool, not a physical prediction. Still, these reflections guide scientists when they consider the nature of the cosmos, because understanding the size and shape of space is essential to understanding its origins, its evolution, and its future. Another layer of repetition arises from the laws of thermodynamics, from the quiet rules that govern energy and entropy, from the way systems evolve over time, and how they sample their possible configurations. In statistical mechanics, any system with finite energy, finite temperature, and finite volume will eventually repeat a previous microstate, if the system is given enough time. This is known as the Poincare recurrence, a theorem that states quietly and mathematically that a closed system, if left alone long enough, must return arbitrarily close to a previous arrangement. The recurrence time is unbelievably long, far longer than any human scale, far longer than the lifespan of stars, far longer than the age of our universe, yet still finite in principle. But our universe is not a closed system, and its expansion prevents such recurrences from playing out on observable scales. And yet the concept influences cosmology, because it hints at how systems explore their possible states, and how repetition, even in finite contexts, emerges from the mathematics of entropy. This brings forth another idea that cosmologists treat with caution, the idea of spontaneous fluctuations in a high-entropy universe, fluctuations that could produce complex structures for brief moments before dissolving back into randomness. Among these hypothetical structures is the notion of a spontaneously formed observer, an arrangement of particles that briefly resembles a conscious entity, produced not by evolution, but by random thermal fluctuation. These hypothetical observers are sometimes called Boltzmann brains. Cosmologists do not invoke them seriously as literal possibilities, but they use the idea as a conceptual test, a way of checking whether a cosmological model produces reasonable statistical predictions. If a model predicts that such random isolated observers vastly outnumber observers formed naturally, then the model is considered problematic, because it implies that typical experience would come from randomness rather than cosmic history. Most modern cosmological models avoid this issue because the accelerating expansion of the universe prevents the kind of thermal equilibrium needed for such fluctuations, and because the large-scale structure of space-time does not remain static long enough for such processes to occur. The idea is mentioned not to provoke fear, but to demonstrate how cosmologists examine repetition, not just through geometry and infinity, but through statistical reasoning, ensuring that models remain self-consistent, logical, and physically grounded. As one moves through these conceptual landscapes, a pattern appears. Repetition arises whenever the possible configurations of a system are limited, and the stage on which they appear is large enough or long enough to hold them more than once. In infinite space, the stage is unbounded. In finite space with unusual geometry, the stage loops around. In statistical mechanics, the stage is time itself, stretching across enormous scales. These perspectives converge into a single idea, that the universe in its vastness is capable of echoing patterns, not as deliberate reflections, but as natural consequences of mathematics. And yet, in all these cases, repetition remains distant, abstract, untouchable. The regions where duplicates might appear, if they exist at all, lie beyond all horizons, forever causally sealed from us, separated by expansion, by time, by the structure of space-time itself. This separation is essential, because it ensures that repetition carries no physical meaning, only conceptual curiosity. There is no influence, no link, no shared information between distant regions. They are as isolated as dreams in the minds of different sleepers, existing simultaneously, but without connection. This disconnect preserves the uniqueness of each region, each galaxy, each world, each consciousness. Even in an infinite cosmos, every observer remains local, bounded within their own horizon, their own thread of experience. Repetition does not diminish individuality, because individuality arises not from pattern, but from location, from continuity, from embeddedness in a specific chain of events. If a distant region contains a world arranged like yours, it does not affect you, does not share your thoughts, does not duplicate your awareness. It is simply a configuration of particles that happens to match, the way the digits of pi contain repeated sequences, without meaning, without narrative. This understanding allows cosmologists to contemplate repetition peacefully, without attributing metaphysical significance, only mathematical structure. It also encourages a calm reflection on the size of the cosmos and the humility that comes with acknowledging how much lies beyond our reach. Even the most powerful telescope is limited by the cosmic light horizon, the boundary determined by the age of the universe and the speed of light. Beyond that horizon, galaxies recede faster than light can travel, carried away by the expansion of space itself. These regions are not in motion through space, but are pulled apart by the stretching of space-time, so that no signal we send can ever reach them, and no signal they emit now will ever arrive. In this sense, the universe we observe is only a small island in a vast archipelago, a finite patch of reality, surrounded by unreachable expanses. Repetition, if it occurs, might unfold in those expanses, quietly, forever unseen. And so Section 4 begins to settle, having followed repetition through infinity, through topology, through entropy, and through the limits imposed by horizons. It leaves us with a single gentle conclusion, that in a universe large enough, Patterns need not be unique, and yet their distance, their inaccessibility, their utter separation makes each moment of lived experience completely its own. A quiet recognition that the cosmos can hold echoes without ever reducing the singularity of here and now. A reminder that even in an infinite reality, each life remains its own unfolding, its own thread, its own irreplaceable narrative. When cosmologists reflect on an infinite universe, a quiet question appears beneath all the mathematics, a question small enough to whisper, yet large enough to shape the entire discussion. If repetition is mathematically inevitable, why does it remain so distant, so unreachable, so abstract? The answer lies in the structure of space-time itself, in the way expansion silences contact between regions, and in the boundary created by the cosmic horizon. The horizon is not a physical wall, not a barrier made of matter, but a limit set by time, the amount of time light has had to travel since the universe began. It marks the farthest distance from which information can reach us, the boundary between the observable universe and the unobservable expanse beyond. Within this horizon, we can see galaxies, clusters, filaments, and the cosmic web stretching across space like a delicate structure of threads. Beyond it, space continues, but the light from those regions has not had time to reach us, and never will, because the expansion of space pushes them away faster than light can compensate. This separation means that even if repetition exists, no observer can ever encounter their supposed twin, or a twin planet, or a twin galaxy. The structure of the cosmos prevents communication, interaction, or influence of any kind. Repetition becomes a mathematical artifact, not a physical overlap. A number on a page, not an event in space, and that distinction matters because it brings the idea back into the realm of calm reflection, gently removing any hint of personal implication. The existence of a distant configuration that resembles you, if such a thing occurs at all, does not alter your life, your decisions, your consciousness, or your identity, because identity is not defined by arrangement alone, but by continuity, by the unbroken chain of experiences from moment to moment, each linked to the next through memory, context, and presence. A distant echo, no matter how similar, lacks that continuity. It exists as a pattern, but not as a self. And so cosmologists describe repetition not as duplication, but as convergence, a convergence of possible arrangements within an unlimited canvas. The distinction is subtle, but essential. Repetition occurs because configurations of matter are finite, while the stage that holds them may be unbounded. It is the same principle that makes certain sequences appear naturally when enough numbers are written, not because the numbers hold meaning, but because the patterns they can take are limited. In this sense, repetition in an infinite universe is a quiet reminder of how mathematics unfolds on large scales, a reminder that infinite systems explore all options, and that even extremely rare events, given infinite room, will appear somewhere. Yet cosmologists remain cautious, because the observable universe, the region we can measure, is finite, and the assumption of infinity remains an extrapolation, a gentle extension of what we know, projected into what we cannot see. Infinity is not proven, only permitted, a possibility allowed by mathematics and consistent with observations, but not required by them. Some models of the universe end after a vast but finite stretch, others curve back upon themselves, others stretch without end. Infinity is allowed but not demanded, and this uncertainty invites humility, a recognition that our understanding of the cosmos is shaped by what the sky permits us to observe, and that the sky, beautiful as it is, only reveals a fraction of what exists. Even in the context of repetition, cosmologists consider alternatives. What if the universe is finite, yet still unimaginably large? What if the universe is finite, yet still growing? What if the universe is finite, but the possible states of matter are so diverse, so numerous, that repetition never occurs in practice? These possibilities show that repetition is not a certainty, only a possibility. One scenario among several competing ideas, each consistent with certain assumptions, each incomplete in its own way. And this is part of the gentle calm of modern cosmology, the recognition that the universe is vast enough to hold many possibilities, yet quiet enough to conceal which of them is true. Beyond geometry and infinity, there is another dimension to repetition, a soft conceptual layer, the role of initial conditions. When the universe was young, its state was determined by tiny quantum fluctuations. variations in density so small that they began as quiet ripples in the early field, yet later grew into galaxies, clusters, and cosmic structure. These fluctuations were random, in the scientific sense, their exact values unpredictable, and because they were random, their patterns would differ across sufficiently separated regions, even if the physical laws remain identical. This randomness adds a layer of uniqueness, a softness that prevents strict repetition from occurring in every scenario. Two regions may share the same physics, the same constants, the same equations, yet diverge simply because the initial seeds were different. Like two landscapes formed by the same forces, yet shaped by different winds, different rains, different quiet influences. This randomness emerges from quantum origins, and it ensures that the cosmos contains variety, texture, and distinction, even across immense distances. In this way, initial conditions act as a gentle counterweight to repetition. They remind us that even in infinite space, repetition is not guaranteed, only allowed. That uniqueness can arise naturally, from chance, from symmetry breaking, from the unfolding of quantum fluctuations across a growing universe. Cosmologists also consider whether the universe might have different large-scale properties in different regions, differences so vast that repetition becomes irrelevant. If inflation occurred in patches, or if the cosmic field had multiple stable configurations, then different regions of the universe could follow different histories, expanding under different conditions, never repeating because their trajectories diverged from the start. In these models, repetition becomes even more abstract, a possibility overshadowed by the chaotic diversity of cosmic formation. Yet even in these scenarios, the mathematical idea remains quiet, patient, rooted in the fact that the space of possible arrangements is finite, and any system with enough room will explore its configuration space fully. Through all these considerations, a theme emerges. Repetition is not a prediction, not an expectation, not a conclusion. It is an implication, a conceptual shadow cast by the mathematics of infinity, a quiet byproduct of thinking in large scales, not an observable phenomenon. And so Section 4 comes to its natural close. Having explored how infinite space makes repetition possible, how topology can create echoes, how thermodynamics introduces recurrence, how initial conditions break symmetry, how horizons preserve locality, and why repetition remains a soft mathematical idea, not a physical event. What remains is a gentle transition, a slow exhale, a quiet movement from contemplation to acceptance. The cosmos is vast enough to hold endless diversity, and simple enough for mathematics to reveal subtle consequences like repetition, symmetry, and recurrence. But the experience of being alive, the experience of observing the universe from a single vantage point, remains unique, unshareable, rooted in the finite horizon that surrounds every observer. In this way, repetition becomes a distant abstraction, while life remains immediate, present, and singular. And with this understanding, Section 4 folds into silence, and the mind becomes ready to drift toward deeper layers of the multiverse, toward dimensions beyond the three we know, toward the spaces where our familiar world becomes a thin surface on a wider reality. The idea of dimensions beyond the familiar three can feel abstract at first, yet when approached slowly and with curiosity rather than urgency, it becomes one of the most peaceful concepts in modern physics. We live in a world shaped by length, width, and height, three directions woven into every object we touch, every movement we make, every landscape we inhabit. But physics has often discovered that what feels intuitive is not the full story. The universe does not owe us simplicity, and yet it offers hints, gentle clues, that reality might be larger than our senses allow. When scientists speak of extra dimensions, they are not referring to imaginary places or fictional portals, but to mathematical directions that could be real, quietly folded or hidden from everyday experience. These dimensions may be compact, curled tightly into scales far smaller than an atom, or they may be expansive, extending outward in ways our bodies cannot perceive. To imagine an extra dimension, it helps to think of a sheet of paper. To an ant walking across its surface, the paper feels like a two-dimensional world, a plane stretching outward with only forward and sideways to explore. But the ant does not naturally sense the third dimension above or below the sheet, even though that dimension is undeniably real. In the same way, our universe may be like a surface, a membrane. embedded in a larger, higher dimensional structure. Physicists call such a surface a brane, short for membrane, and in many models, our entire cosmos is a three-dimensional brane floating in a higher dimensional space. We do not feel the extra dimensions directly, because the particles and forces that make up our world, electrons, quarks, photons, may be confined to the brane itself. Like ink on a sheet of paper, they move freely within the surface, yet remain bound to it. Only one force seems to behave differently: gravity. Gravity silhouettes the universe on vast scales, shaping galaxies, bending light, guiding motion across billions of light years, yet it is astonishingly weak compared to the other fundamental forces. A tiny magnet can lift a paperclip upward against the entire gravitational pull of the Earth, a reminder that gravity's influence is strangely diluted. One idea suggests that gravity is not weaker, but simply spread out, leaking into extra dimensions, diluted across a larger geometric space. If the gravitational field extends beyond the brane, while other forces remain confined, its apparent weakness becomes more understandable. In this picture, our universe floats like a luminous sheet, while gravity drifts softly through a higher dimensional ocean. Researchers call that higher space the bulk, a realm spacious enough to contain many branes, not just one. A brane is not merely a thin sheet, but a dynamic, flexible object, capable of stretching, rippling, or drifting. Some branes might be parallel to ours, subtly separated by distances too small for us to notice or too large for light to bridge. These parallel branes could be other universes, each with its own particles, its own forces, its own version of physics. Some might be barren, others rich with structure, some similar to our own, others governed by different constants. Most would remain forever unreachable, yet still part of the same higher dimensional landscape. The idea becomes even more intriguing when considering cosmology. In certain models, what we think of as a Big Bang might have been a collision between branes, a higher dimensional event that released tremendous energy, transforming into matter and radiation within our brain. Two branes drifting gently through the bulk, like vast, quiet sheets, could have brushed against each other or collided more forcefully, igniting a universe. In that picture, our cosmos is not the only one formed this way. Other collisions could occur elsewhere in the bulk, giving birth to other universes on other branes. These universes would not be separate bubbles within one infinite space, as in inflationary models, but parallel layers, stacked or drifting through dimensions we cannot perceive. Some theories imagine the bulk as a vast serene expanse, with countless branes suspended like leaves on a calm pond. Others imagine branes as dynamic, fluctuating sheets, constantly moving and sometimes interacting. In either case, the multiverse becomes a geometric reality, a consequence of higher dimensions rather than of branching quantum states or cosmic inflation. Our universe's three-dimensional appearance is not the whole story, but only the slice we can directly explore. When imagining higher dimensions, it is easy to picture something chaotic or mystical. But the mathematics behind these models is grounded in the same physics that describes the particles and forces we study today. String theory in particular requires extra spatial dimensions, because the vibrations of fundamental strings, the tiny filaments proposed as the building blocks of reality, depend on a higher dimensional context to behave consistently. Just as a guitar string needs room to vibrate, a fundamental string needs room in the form of additional spatial directions. Different vibrational modes correspond to different particles, giving rise to the zoo of matter and forces we observe. But those vibrational patterns only work if space has more than 3 dimensions. It is not a preference, but a mathematical requirement. If those extra dimensions were large, we would see them. Objects would move in unexpected ways. Gravity would behave differently. Light might spread into unfamiliar paths. But if extra dimensions are curled tightly, wrapped into structures far smaller than any particle we can detect, they would remain hidden, present but inaccessible, like a rolled-up thread invisible to the ant walking across it. In some models, however, the extra dimensions are not small at all. They could be large, perhaps even infinite, yet still hidden from us because we are confined to our brain. Imagine living on the surface of a lake and being able to move only along that surface. The water below and the air above exist. They are vast, but they are not part of your accessible world. A higher dimensional universe might be similar. We inhabit the surface, but the depth around us remains untouched. One of the most striking implications of brain models is that two universes could be separated by a distance smaller than a fraction of a millimeter, yet entirely invisible to each other. Light cannot cross the gap, particles cannot leap from one brain to another, and only gravity, soft and elusive, might drift between them. This leads to a quiet possibility that our universe has neighbors. Parallel worlds not metaphorical, but physical, lying alongside ours in a geometric dimension we do not experience. Some might have different physical constants, leading to entirely different forms of matter. Some might be sterile, cold, or empty. Others might resemble ours closely, not through repetition of infinite space, but through the physics of higher dimensional symmetry. If brains can collide, they can also separate, drift apart, or oscillate. Some models of cosmology imagine a rhythmic universe, where brains periodically approach, touch, and recoil, each encounter creating a burst of energy similar to a Big Bang. In these scenarios, time does not begin with one creation event, but with cycles of cosmic contact, long epochs of quiet separation punctuated by moments of luminous birth. From a sleep-friendly perspective, these ideas are not meant to stir urgency or concern, but to invite a sense of scale, a recognition that reality may be far more spacious than everyday life suggests. The softness of higher dimensional geometry brings a sense of calm. Even the complexities of string theory can be seen as a gentle reminder that the universe is not limited by our intuition, and that the deepest layers of reality may be quiet, elegant, and serene. In some models, there are 11 dimensions, with our brain occupying 3 of them, and the rest forming a hidden scaffolding for the laws of physics. In others, the number of dimensions could be even higher, or arranged in intricate topologies, spaces within spaces, folded shapes that influence how particles behave. Every possibility expands the landscape of the multiverse. Because if higher dimensional space exists, there is no reason for there to be only one brain. Multiple brains could coexist, each one a universe, each one with its own physics, each one drifting in the quiet expanse of the bulk. Some may be close, some distant, some interacting, some isolated for eternity. Our universe might be a single glowing sheet, one membrane among an unknown number, each carrying its own galaxies, its own histories, its own outcomes. Even the concept of distance becomes more nuanced in higher dimensions. A universe could be unimaginably far when measured along the brain, yet extremely close in a higher dimensional direction. Like 2 pages in a book, their surfaces large and separate, yet their separation in the third dimension small and silent. This gives rise to speculative ideas about how universes might influence each other. Could gravity from a nearby brain subtly shape structure in our own? Could dark matter be a shadow of matter confined to another brain, its gravity drifting through the bulk? Some researchers have explored these possibilities, and though they remain unproven, they offer peaceful avenues of thought. The elegance lies not in claiming certainty, but in allowing the mind to rest in possibility. Higher dimensions are not required for the multiverse, but they provide one of its most mathematically grounded forms. As we move deeper into this conceptual landscape, the lines between geometry, physics, and cosmology blur gently, creating a unified picture where universes arise naturally from the structure of space itself. When the mind drifts through these ideas at night, they can feel soothing rather than overwhelming. Not because they are simple, but because they open room for wonder, and because they remind us that our familiar world is part of a vast, layered, and softly interconnected reality. As the thoughts settle, and the image of drifting brains lingers, we approach the quiet boundary where Section 5 begins to resolve, and where the next themes of emergent reality will eventually unfold. When we slowly let the mind settle into the idea of higher dimensions, a gentle shift begins to happen. The familiar 3-dimensional world feels less like the full shape of reality, and more like a thin cross-section, a slice of something deeper. Mathematically, dimensions are simply directions in which something can move. Nothing mystical, nothing dramatic, just additional degrees of freedom. In 3 dimensions, a point can shift forward and back, left and right, up and down. A 4th spatial dimension would be another direction entirely, perpendicular to all the others, beyond anything our senses can detect. Even though we cannot experience that direction directly, physics allows us to describe it, to calculate with it, and to explore how it might shape the universe we do see. Many models envision these extra dimensions as compact and curled, so tightly wound that even the smallest particles cannot move through them. But other models imagine them as wide and open, allowing gravity to extend beyond our brain into the larger dimensional bulk. This possibility offers a peaceful explanation for one of the deepest puzzles in fundamental physics: why gravity is so much weaker than the other forces. It is not that gravity lacks strength, but that its influence spreads into additional directions, moving silently through dimensions our instruments cannot reach. The force we feel on the brain is only a fraction of its full higher dimensional shape. In this sense, gravity becomes a messenger between worlds, a field that does not respect the boundary of our brain. It ripples outward, filling the bulk and potentially brushing against neighboring universes. These neighbors, if they exist, would not orbit our stars or lie beyond our galaxies. They would not be further away in ordinary space, but displaced in a higher dimensional direction. Close, yet unreachable. Present, yet invisible. Even if an entire universe lay a fraction of a millimeter away along a higher dimensional axis, we would not see its light, or feel its matter, or detect its radiation. The electromagnetic field and the particles that carry it remain confined to the brain. Only gravity, soft and subtle, would drift between the layers. Some physicists have proposed that dark matter could arise from matter located on a parallel brain. We would not see it, we would not touch it, but its gravity might extend through the bulk, slightly influencing our own universe, shaping galaxies, bending space-time, leaving only gentle footprints. If true, dark matter would not be dark at all, but simply displaced in a dimension we cannot access. This idea remains unproven, yet it fits naturally into the language of brain cosmology and adds another thread to the tapestry of possible multiverse structures. Other models imagine brains that are not static or fixed, but dynamic and alive with motion. They might undulate gently like sheets of fabric carried by a slow breeze, or drift with immense stillness through the higher dimensional expanse. If two such brains pass close to each other, their gravitational pull could create subtle distortions, warping geometry in both universes. If they were to collide or even brush against one another, the energy released could resemble a Big Bang, filling both brains with radiation and matter. In such a picture, the birth of our universe becomes not a singular eruption, but a higher dimensional event, a moment when two immense surfaces touched. The radiation and particles we observe today would be relics of that cosmic encounter. Our expanding universe would be the aftermath of a collision between brains. Other brains could have collided elsewhere in the bulk, creating other universes with different histories, different structures, and different flows of time. The idea may sound speculative, yet it arises naturally from the mathematics of higher dimensional theories and provides a peaceful, elegant alternative to traditional cosmological models. In this view, the multiverse is not an infinite foam of bubbles or a branching set of quantum pathways, but a layered arrangement of membranes, each universe a surface, each surface floating in a larger ocean. This layered structure invites gentle analogies, like pages in a book, side by side yet containing separate stories, separate worlds, separate timelines, close enough to touch in a higher dimension, yet entirely isolated within the brain, or like sheets of ice on a frozen lake, stacked, shifting, occasionally cracking or merging, each with its own delicate pattern, or like veils in a quiet room, thin, light, and drifting. You sense their presence, but cannot see through them. These analogies are imperfect, yet they help frame the idea that our universe may not be the only structure woven into the higher dimensional fabric. The mathematics also suggests that the bulk may contain regions where dimensions are shaped differently. Some may be curled tightly, some may be broad, some may host many brains, some may be empty. It is not a uniform landscape, but a varied and intricate architecture. Our brain may be one among countless others, spread across an expanse that itself defies ordinary language. In higher dimensional space, the notion of distance changes. Two universes could be far apart within the brain, yet only a hair's breadth apart in the bulk, their separation small but their interaction forbidden. Even time itself might have different properties in different layers of the bulk. Some brains could expand faster than ours, others might contract, some might have freezing, silent epochs, while others flow with constant transformation. Not all brains need to resemble our universe. Some might have more spatial dimensions than 3. Some might have fewer. Some could host forms of physics that do not permit stars or galaxies to form. Some could be rich in structure yet remain forever invisible to us. Because the forces that shape these brains depend on how dimensions are arranged. The bulk becomes a quiet stage where different universes unfold with different rules. Our presence within this larger structure is both humbling and soothing. We are part of a geometry so vast that it may contain countless worlds drifting in silence. Yet nothing about this idea demands worry. The brains do not threaten one another. They do not collide frequently. They do not destabilize easily. To the contrary, the mathematics implies stability. Brains settle into configurations that persist for immense spans of time, like floating sheets that find calm equilibrium in a tranquil sea. Every universe remains itself, carrying its own galaxies, its own quiet evolution. Some models also suggest that fluctuations in the bulk could cause brains to move closer together or drift apart slowly across cosmic ages. But such motion would be unimaginably slow, gentle beyond comprehension, occurring over timescales far greater than the lifetime of stars. In this sense, higher dimensional cosmology adds serenity to the multiverse idea. It invites us to imagine a cosmos not tense or chaotic, but spacious, soft, and layered. A calm architecture where worlds coexist without conflict. A quiet physical reality where the laws of nature arise from the geometry of hidden dimensions. A setting where the origins of our universe might be part of a broader, deeper story. A story written not in one space, but in many. As these thoughts drift through the mind, they create a sense of openness, an awareness that our familiar world is part of something broader, but not in a way that demands urgency. Instead, the awareness invites rest and a gentle curiosity. And as this segment of the exploration settles, the ideas of brains and higher dimensions come to a natural pause. The picture is wide, but it begins to complete its shape. In the quiet language of higher dimensional physics, there is a gentle but profound realization that what we call the universe may simply be the part of reality that is able to shimmer into our senses. The deeper structure, the place where our universe rests, may be vast, smooth, and invisible, a dimensional ocean beneath the surface of everything. As we linger in this idea, the mind begins to loosen its usual boundaries. It makes room for the possibility that our familiar three-dimensional world is only one configuration in a much richer arrangement. Not the center of existence, not the default, just one thread in a wider geometric tapestry. In this wide geometry, brains do not behave like rigid sheets of material. They are flexible, responsive, shaped by fields and forces that extend through the bulk. They can tremble gently with tiny quantum vibrations, or curve smoothly around each other in ways that our spatial intuition cannot quite imagine. To picture such motion, it helps to think of surface tension on liquid. A droplet forms a rounded shape because that shape minimizes its energy. In a similar way, a brain may curl, bend, or flatten depending on the fields present in the bulk. These motions are not rapid. They would occur over timescales longer than the lifespan of galaxies. The brain we inhabit would feel utterly still as the night sky appears even though stars move constantly. Even the presence of matter on the brain can influence its shape. Mass slightly warps space-time in our familiar dimensions, but in higher dimensional theories, mass can also tug on the brain itself, creating smooth deformations that extend into the bulk. This reshaping is subtle, like the faint ripple that spreads across water when something light touches its surface. The brain adjusts, redistributing tension, finding equilibrium. And if other brains exist nearby, their shapes could influence one another through the gravitational field in the bulk. Not by exchanging particles, but by sharing geometry. Even without touching, two brains could subtly curve toward each other or push apart depending on the energy stored between them. Some models suggest that our universe may have once been closer to another brain than it is now. The separation between brains could have been smaller in the distant past, allowing energy to flow more freely or amplifying fluctuations that shaped early cosmology. Other models imagine the opposite, that our brain began with almost no separation from another and slowly drifted apart. In this view, the separation is not constant, but evolves with time. That evolution could change the strength of certain interactions on the brain. It could alter the effective amount of dark energy. It could reshape the rate of cosmic expansion in subtle, graceful ways. The idea that dark energy could arise from brain dynamics is one of the most elegant interpretations offered. Instead of a mysterious force permeating empty space, it becomes a geometric effect from the tension or curvature of the brain itself, or from fields that stretch between brains. A gentle tension in the bulk might pull our brain outward, causing the accelerated expansion we observe. If this interpretation is correct, then the fate of our universe is tied not only to its own internal physics, but also to the hidden geometry surrounding it. Such a possibility gives the cosmos a quiet, expansive feeling. We are not floating in empty space, but lying softly within a larger shape, a membrane supported by deeper dimensions. Some researchers have explored whether tiny defects in the brain might lead to observable phenomena. A small irregularity or twist could create localized effects that mimic exotic particles or unexplained gravitational signals. If the brain were slightly folded in some region, two distant parts of our universe might be closer in the bulk, even though they are far apart within the brain. This could leave gentle imprints in the cosmic microwave background, subtle alignments, or slight deviations from perfect statistical randomness. Searching for these signatures has become a calm, ongoing effort in observational cosmology. Nothing definitive has emerged, but the exploration continues with the same quiet curiosity that shapes the spirit of this narration. An especially intriguing possibility is that gravity might occasionally leak more dramatically into the bulk under extreme conditions. At very high energies, perhaps near black holes or in the early universe, the fabric of the brain might flex enough to allow gravitational energy to flow outward. Such leakage could weaken gravitational signals we expect to observe, or alter the pattern of gravitational waves moving through our universe. Experiments have been proposed to look for missing gravitational energy, an indication that some of the field has slipped out of the brain and into the bulk. So far, no such loss has been detected, but the idea remains open. There is also the possibility that particles interacting very weakly with matter could cross into the bulk. Perhaps neutrinos, already mysterious and elusive, could oscillate into higher dimensional states and return in altered form. This idea remains speculative, but it shows the range of questions that higher dimensional physics allows us to ask. And then there is the gentle, striking idea that our universe could resonate. A brain has tension, and a surface with tension can support vibrations. These higher dimensional vibrations would not be like sound in air or waves on water, but oscillations of the brain's position in the bulk. Such oscillations could have occurred in the early universe when energies were immense. They might have left faint traces in the distribution of galaxies or in the spectrum of gravitational waves passing through space-time. Each possible vibration corresponds to a higher dimensional mode, a pattern of motion touching both the brain and the bulk. These modes may even give rise to particles we can detect, their energy appearing as mass in our three-dimensional world. The brain, in this sense, is not merely a stage for the universe to unfold upon. It is a dynamic structure that shapes what kinds of particles and forces can exist. If the brain were arranged differently, if its tension were higher or lower, if its curvature were sharper or softer, the resulting physics would be transformed. The particles we see are deeply linked to the geometry of the brain. This idea harmonizes with the broader vision of higher dimensional theories. Reality becomes a gentle conversation between geometry and physics, a quiet interplay between shape and law. The forces we observe are not arbitrary. They emerge from the underlying structure of the brain and the bulk. The brain could be thought of as a kind of cosmic instrument, and the particles within it are the notes produced by its vibration. Change the instrument, and the notes change. This is one of the most elegant aspects of brain cosmology. It explains variation in physical laws without requiring each universe to follow a random set of rules. Instead, each universe is the natural consequence of its brain's geometry. Parallel brains may host universes with slightly different shapes, slightly different tensions, slightly different curvatures. These differences could yield different masses, different interactions, different cosmic histories. Some brains may host universes rich with structure, filled with stars and galaxies. Others may remain dark and silent, their laws too simple or too restrictive to allow complexity to form. In this vision of the multiverse, variation is natural, gentle, and geometric. And as our exploration approaches the final themes within Section 5, the last major idea emerges softly. If brains can drift, if they can collide, if they can carry entire universes upon them, then the ultimate question becomes whether these interactions could repeat. Could universe-creating collisions occur more than once? Could cycles of contact and separation shape an endless sequence of new brains, new cosmoses, new epochs? In some models, the answer is yes, a slow rhythm of creation stretching across the bulk. But even if such cycles exist, they unfold on timescales so enormous that our entire cosmic history is only a tiny moment within them. There is no urgency in their movement, only stillness and vastness, and a quiet sense that reality might be deeper than any single universe can reveal. With this final reflection, the exploration of higher dimensions and brain worlds reaches its natural resting point. There is a gentle shift as we move from higher dimensional brains into the idea of reality as something that might not be fundamental, but emergent. A structure that appears solid and continuous when viewed from within, yet built from deeper rules beneath the surface. In physics, emergence describes the way complexity grows from simple foundations. Snowflakes, waves, crystals, galaxies, all rise from underlying patterns that do not themselves resemble the structures they create. A single water molecule is not a wave, not a tide, not a spiral of turbulence. But the interactions of many together give rise to motion and form that feel completely different from the ingredients. This same principle may govern the most fundamental aspects of reality: space, time, particles, laws, all potentially emerging from something more abstract. Some physicists describe this deeper layer as information, not information in the ordinary sense, like words or messages, but as the raw capacity for distinctions to exist, the ability for something to be different from something else. In this view, reality becomes a quiet computation, a slowly evolving pattern of encoded relationships. The universe is not running on a computer. Instead, the universe behaves as if it is implementing rules similar to those used in computation, rules that allow complexity to appear from simple operations repeated many times. One way to imagine this is through cellular automata, mathematical grids where each point updates itself according to a small set of rules. The rules are simple, yet the result can be astonishingly intricate. Patterns ripple, merge, divide, forming structures that seem alive despite their mechanical origin. Some researchers have wondered whether space-time itself operates in this manner, whether the smoothness we perceive is an illusion of scale, and beneath it lies a lattice of microscopic updates, tick by tick, moment by moment. The gears of this underlying layer would not be visible directly, just as a fluid seems continuous even though it is made of atoms. Space-time might seem smooth even though it is composed of discrete informational units. If this is true, then the laws of physics are not arbitrary commands but consequences of the rules that govern how the underlying information evolves. Gravity, electromagnetism, quantum fields, all emergent, not imposed from outside, but arising naturally from the structure of the informational substrate. This idea transforms the concept of a universe. A universe is no longer simply a region of space filled with matter. It becomes a program of sorts, a process, a vast unfolding pattern played out across a substrate beyond our direct perception. In such a vision, different universes might correspond to different sets of rules, different starting conditions, different structures encoded into the underlying layer. Some universes could have rules so simple that nothing complex ever forms. Others could produce endless turbulence with no stable structures. Only certain rules would give rise to matter, chemistry, stars, life. And perhaps our universe is one such rule set. The possibility that different universes arise from different informational laws creates a gentle bridge between the multiverse concept and the idea of emergence. The multiverse need not be spatial. It can be conceptual. a variety of possible rule sets, each giving rise to its own reality. Each universe a different blossom on the same underlying tree of information. Some physicists explore whether quantum mechanics itself might be an emergent phenomenon, that the strange behavior of particles does not arise from inherent mystery, but from the collective statistics of deeper informational elements. In this view, the wave function is a description of our knowledge about the underlying system, not the system itself. The apparent randomness comes from averaging over many microstates that we cannot see individually. Others imagine quantum mechanics as truly fundamental, with information existing in the wave function itself. Reality then becomes a continuous computation, each quantum interaction updating the informational state of the universe. These are delicate ideas, still forming, still shifting, but they invite us to slow down and consider a universe that is not built from things, but from descriptions, from relationships, from the quiet hum of information being processed. It is a peaceful thought that the universe is not chaotic but deeply ordered, an immense and serene calculation unfolding without haste. The simulation hypothesis is sometimes confused with these ideas. Popular imagination often treats it as if our universe were running on a machine created by another civilization. But scientific treatments are far more subtle and do not require external programmers or artificial machinery. Instead, they explore the possibility that computation is simply what the universe does, that the laws of physics are equivalent to update rules of a natural process. No one needs to design it. No one needs to observe it. No one needs to press start. The process simply exists as the natural state of things. Nevertheless, the hypothesis that intelligent beings could simulate a universe remains a topic of discussion. Not because it must be true, but because it raises deep questions about the nature of reality and the limits of inference. If a civilization had access to enormous computational resources, they might simulate physics down to extremely small scales. If the simulation were large enough and detailed enough, the emergent structures inside might not be aware of the computational substrate. They would observe consistent laws, stable particles, predictable interactions. They might even discover mathematics that describes their universe's behavior with extraordinary accuracy. This leads to a gentle and contemplative possibility that beings inside a simulated universe could develop their own science without ever detecting that their reality rests on another layer. If this were the case for us, how could we know? What signs would exist if reality were encoded? Some physicists imagine that the granularity of the underlying grid might leave tiny anisotropies in the behavior of particles traveling at high energies. Others suggest that the finite nature of a computation might manifest as limits on the precision of physical constants. It is important to emphasize that no evidence currently supports these speculations. They remain gentle thought experiments, explorations of possibility rather than conclusions. But the spirit of the inquiry is peaceful. It does not claim that we are simulated, but considers what reality means if information is the true foundation. In this sense, even if the universe is not simulated, it may still be computational. Its laws may still arise from underlying informational rules. Its structures may still be emergent from deeper simplicity. Emergence has a calming beauty to it. It suggests that complexity does not need a complex origin, that the vastness of galaxies can arise from simple rules just as music can arise from simple vibrations. There is comfort in the idea that the universe evolves according to principles that are elegant and minimal. And if different universes exist, each emerging from its own rule set, then the multiverse becomes an exploration of all possible computations. Each universe a different expression of the underlying informational substrate. This brings us gently to one of the most profound ideas within emergent reality. Time itself may be emergent. The flow of moments, the feeling of before and after, the unfolding of events, all may arise from correlations between informational states, not from a fundamental river of time, but from relationships between successive configurations. The universe does not move through time. Instead, time is the ordering of informational updates, a quiet sequence of states following states. This view relaxes the mind into a sense of timelessness, where the present moment is simply the current configuration of the informational substrate. In such a universe, the past is not gone, The future is not yet real, and the present is the only layer being actively computed. This idea aligns gently with the block universe picture of relativity, while giving it a computational flavor. The present becomes a softly illuminated frame, surrounded by the stillness of unrealized possibilities. Another implication is that consciousness may itself be emergent, not separate from physics, but arising naturally from the complexity of information processing. In this view, a mind is a pattern, a delicate structure maintained by the brain as it processes information. Conscious experience emerges from this pattern in a way we do not yet fully understand. This does not diminish consciousness. It embeds it in the deep structure of the universe's computation. A mind becomes a shimmering arrangement of informational processes, as natural as the motion of planets or the formation of stars. This perspective does not claim to solve consciousness. Instead, it places consciousness within the same quiet mystery as the cosmos, a phenomenon that arises from deeper rules we are still learning to decipher. As we approach the final elements of this section, the ideas begin to connect. Emergence, information, computation, multiverse. All are different ways of exploring the same question. What is the most fundamental layer of reality? Is it space, time, fields, particles, geometric structures, or the quiet logic that shapes them? If information is the deepest layer, then the multiverse might simply be the set of all ways information can be arranged. Each universe a different pattern, a different rule set, a different unfolding, and our universe one serene expression among countless others. With this reflection, the discussion of simulated universes and emergent reality settles into stillness. There is a quiet shift that happens when we begin to think of reality not as a thing, but as a process, not a fixed structure, but a continuous computation. Something that is not stored, but generated, moment by moment, as information flows through rules so simple that their simplicity feels almost deceptive. Because when physicists talk about emergent reality, when they speak of the universe as something produced by underlying informational dynamics, they are not talking about a giant computer with wires and fans, or a cosmic machine humming on a table. They are speaking of mathematics that behaves like a computation, laws that unfold like programs, patterns that arise the way images form from pixels obeying rules. And they are suggesting that what we call the universe may be nothing more than the stable, large-scale pattern generated by those rules running for a very long time. This idea often begins with cellular automata, simple grids of cells that follow simple instructions. If this cell has these neighbors, turn on. If it has those neighbors, turn off. Rules so basic that a child could write them, yet they give rise to shapes that grow, split, move, collide, and form structures that look strangely alive. John Conway's famous automaton called The Game of Life is the usual example, a tiny world where clusters of pixels behave like creatures, gliding across the grid with the grace of organisms. No one programmed those behaviors. They emerged. They were simply what happened when a rule was followed over and over in a space large enough to let complexity breathe. And this is the key insight behind emergent reality, that the laws of physics might be the simplest possible rules capable of producing self-consistent structure, space, time, matter, and consciousness, when allowed to run across something that behaves like a computational fabric. Some physicists speak of space-time as an information network, a web of discrete points connected by links that carry bits of data. The geometry we see emerges from the pattern of those connections. The flow of time emerges from the update rule that decides how those connections shift and evolve. Even gravity might be an emergent force, a natural consequence of how information arranges itself in a system trying to maximize entropy. In this view, nothing is truly fundamental except the information and the rules. Particles are not little beads flying through space. They are stable patterns inside the informational flow, recurring configurations that persist the way a melody persists even though the air molecules carrying it are constantly changing. A particle is a process, not a thing. A field is an algorithm running everywhere at once. A law of physics is a rule in the code that cannot be broken because it is not a preference, it is the definition of the system itself. This idea dissolves boundaries. Matter and energy become interchangeable not as a metaphor, but as two sides of the same informational structure. Space and time become properties that arise from the pattern, not containers that must be filled. Even causality can be understood as the orderly propagation of updates from one region of the code to another. And if this is true, if the universe is a computation, a natural question follows softly. Is the computation literal or merely mathematical? Is there a substrate beneath the substrate, some deeper layer where the information resides and the rules are stored? And if such a layer exists, would it be physical in any sense we understand, or would it be something entirely outside the categories we use to describe experience? Some scientists prefer the gentle version of this idea, the one that does not require a simulator or a purpose. They say that a universe based on information is no different from a universe based on particles. It is simply a different description of the same thing. The universe would not be a simulation, but a self-contained informational structure existing for no reason other than that it can. A consistent pattern that needs no designer, no programmer, no external computer, just a set of rules and the space to let those rules unfold. In this softer interpretation, emergence is simply how complexity grows from simplicity, how galaxies arise from fluctuations, how life arises from chemistry, how consciousness arises from the quiet electrical waves flowing through neural networks. And in this interpretation, the multiverse appears naturally, because many sets of rules are possible. If different initial conditions or different underlying instructions can generate different emergent worlds, then anything capable of existing within the space of possible rules may exist somewhere in the grand landscape of computational realities. But there is also a sharper version of the idea, one that people often imagine when they hear the word simulation. A version where our world is a deliberate construct, a modeled environment, running on some deeper substrate we cannot access. In this version, our universe is not emergent from purely mathematical rules, but is intentionally instantiated inside a computational medium. Like characters in a video game who move and think and interact within a world built from lines of code. But the scientists who entertain this possibility do not imagine a programmer sitting behind a screen. They imagine civilizations so far beyond ours that their technologies are indistinguishable from nature, capable of simulating physics with such fidelity that particles obey quantum mechanics at every scale, capable of creating consciousness not as an illusion, but as a consequence of information complexity. To such beings, creating a universe might require no more effort than writing a line of code or adjusting the parameters of a mathematical model. They might not simulate worlds for entertainment or curiosity. They might simulate them to understand physics, to explore cosmology, to see how different universes evolve when different rules are chosen. In that sense, a simulated universe would be no more artificial than a mathematical structure proven to be self-consistent. It would simply be a way for information to express itself. But the deeper and more sleep-soft question is not whether our universe is literally simulated. It is whether simulation and emergence are meaningful differences at all. If a world behaves like a computation and unfolds like a computation and is structured by the same logic that governs computation, then it might not matter whether it lives inside a machine or exists as pure mathematics. The experience from within would be exactly the same. The laws would be the same, the constants, the particles, the fields, the geometry, the quiet expansion of space-time. We would still see sunsets and galaxies and the soft microwave glow left behind by ancient light. We would still wonder what consciousness is and why existence feels the way it does. We would still ask why there is something instead of nothing, and why the something is arranged in such a delicately balanced way that complexity can form at all. Emergence tells us that complexity is not rare, nor fragile, nor mysterious. It is inevitable when simple rules are given enough room to play. Life, mind, structure, order, and chaos all become natural consequences of informational flow. And when physicists explore the multiverse through this lens, they are not imagining other universes made of different atoms or different energies. They are imagining other universes generated by different rules, rules that might lead to universes simpler than ours or far more complex. Universes where dimensions evolve dynamically, where forces shift over time, where matter never forms or forms into patterns we cannot even imagine. Some universes may flicker into existence and vanish instantly, their rules incapable of sustaining stable structure. Others might blossom into infinite complexity, unfolding like fractals built from equations we have not yet discovered. And some may be so profoundly different that our language has no way to describe them. But they all fit within the same soft idea. That reality is what happens when information is allowed to breathe. And so as we drift through this thought with no urgency and no need for definite conclusions, we rest in the possibility that our universe is one expression of a deeper informational ocean, a shimmering field of potential rules and possible worlds, a sea of realizable structures, each emerging from the quiet dance between logic and possibility. And when our universe was born, when its rules were chosen, when its constants settled, it became not the only world, but one world among many, a single pattern in an infinite space of patterns, a melody in an endless library of songs. And as this section of your nighttime exploration comes to a close, we cradle the idea that reality may be emergent, may be simulated, may be informational, may be one structure in a far larger landscape of possible structures. And we let that idea rest gently inside the mind like a soft, unfolding question, a question with no pressure to be answered, a question that simply invites wonder, before we drift quietly into the next realm of the multiverse, the realm of limits, horizons, and the soft edges of what can be known. There is a quietness that arrives when we step into the idea of limits, not limits as barriers, but as tranquil horizons, boundaries that define what can be known and what remains forever beyond the reach of any experiment or observation. In science, a limit is often not a wall, but a soft edge, a point where certainty fades into probabilities and then into silence. And when we examine the multiverse through this softer lens, we find that limits are not failures or shortcomings. They are part of the structure of reality itself. They are the reason the universe feels vast, mysterious, and endlessly open to gentle wonder. Some of the strongest limits come from the nature of space-time. Our universe has a horizon, a distance beyond which light has not had enough time to reach us. It is not a metaphorical horizon, not a poetic idea, but a real physical boundary, an edge of visibility created by the finite speed of light and the finite age of the cosmos. Everything beyond that horizon exists, but is forever inaccessible, not hidden by clouds or darkness, but by the geometry of space-time. Even if the universe lasts for trillions of years, some regions will never be connected to us by any signal. They are simply too far, moving away too quickly, carried by the expansion of the cosmos. And so no matter how advanced a civilization becomes, no matter how powerful their telescopes or technologies, there are parts of reality they can never see. Limits woven directly into the fabric of the universe. And these horizons shape our understanding of the multiverse. Because if other universes exist beyond our cosmic bubble, or if regions of space are eternally out of reach, then no measurement can ever confirm them. Not because the ideas are wild, but because the structure of space-time makes them silent. This is one of the deepest forms of scientific humility, the quiet knowledge that some things will always remain invisible. We can infer, speculate, model, and reason, but we cannot cross the horizon. We can only stand at its edge and let the imagination flow gently outward into the unseen. Quantum mechanics introduces another kind of limit, a softer one, but just as profound. In the quantum world, possibilities exist in superposition, many outcomes coexisting as potentialities. But once a measurement is made, those possibilities decohere, and only one branch continues in our experience. The others, if they exist, drift silently away in the vast branching structure of the many worlds view. But no branch can communicate with another. No device can detect the presence of a neighboring outcome. The branches separate cleanly, quietly, forever. A limit not of distance, but of interaction. A limit not imposed by technology, but by the laws of quantum decoherence. Even if the multiverse of quantum outcomes is real, every branch must remain a private thread of the cosmic tapestry. The separation is absolute. The isolation is perfect. And because of this, the many worlds multiverse can never be tested in the usual sense. It is not hidden behind a horizon, but beyond communication. A different kind of silence. Mathematics adds a third limit, one that does not come from physics, but from logic itself. There are statements that are true, yet cannot be proven within the system they belong to. There are structures that exist, yet cannot be fully described by any finite set of axioms. This is not a flaw in mathematics. It is a property of all sufficiently powerful logical systems. And so when we ask questions about the multiverse, questions like, why these laws and not others? Why this universe and not a different one? Why existence took this shape instead of another? We might be asking questions that are mathematically meaningful, yet forever unanswerable from inside the system we inhabit. Limits not imposed by distance or physics, but by logic, by the structure of reasoning itself. These three limits, cosmic, quantum, mathematical, intertwine gently. They hint that reality has boundaries built into its foundation, boundaries that protect the mystery, that preserve the vastness of the unknown. And when scientists study the multiverse, they often find themselves standing in a quiet space between knowledge and wonder. They recognize that some questions may have no experimental answer. Not because we are too early in our development, not because our instruments are too primitive, but because the questions point beyond the realm of what can ever be measured. And yet, that does not diminish the beauty of asking them. In fact, it might be the reason we feel such awe when we contemplate the multiverse. Because we sense there is more than we can ever grasp, more than any species can ever discover, more than any theory can ever contain. A horizon not of light, but of understanding. An ocean with no far shore. Even the idea of physical law contains a limit. We do not know whether the laws of physics are truly fundamental or whether they emerge from deeper rules, or whether deeper rules emerge from something deeper still. The chain of explanation may not have an end, or it may end abruptly at a boundary we cannot cross. Perhaps the laws we see are one option among infinitely many, selected randomly, or selected by stability, or selected because only some allow complexity to arise. Or perhaps there is no selection at all, no deeper reason, no underlying cause, just the quiet fact that our universe is one of the possible universes that can exist, and that we are here to observe it. The limits of knowledge are not obstacles to be conquered. They are features of a universe that invites curiosity without demanding certainty, a universe that allows us to understand much, but not everything, a universe that leaves space for dreaming, because if everything could be known, if the cosmos revealed all its secrets without reservation, wonder would fade, mystery would disappear, and the universe would feel smaller. The not knowing is part of the beauty. The unanswered is part of the calm. The unreachable is part of what makes the night sky feel so deep, so infinite, so quietly alive. So as we rest in this seventh realm of the multiverse exploration, we soften into the understanding that limits are not failures. They are invitations. Invitations to imagine what lies beyond, even if we can never see it. Invitations to reflect on how remarkable it is that we can know anything at all, in a universe built upon silence and possibility. Invitations to accept that certainty is not required for peace. And with this acceptance, we drift gently to the final horizon, the closing reflection, the soft epilogue, where the journey through infinite worlds settles into quiet stillness. There is a point where the mind becomes gently aware that not everything can be captured by thought or by measurement or by the quiet reach of theory, a place where understanding simply dissolves into soft unknowing. And yet, this unknowing is not an absence. It is a presence of its own, a space where curiosity rests without pressure. Science meets this space often. Whenever a boundary emerges, whenever a limit of observation or inference becomes clear, the universe seems to whisper that some truths are woven too deeply into the fabric of reality to be pulled free. One of these limits is tied to energy. Every act of measurement requires energy. Even the most delicate observation changes the system ever so slightly. To observe perfectly would require infinite energy, and infinite energy is something the universe does not permit. So every measurement carries a softness, a blur, a veil of uncertainty that can never be fully removed. This is not a flaw. It is simply how nature keeps its balance, how it prevents any observer from ever extracting more information than the cosmos can allow. Even time itself places limits on knowledge. To know everything about a system requires watching it for long enough that every pattern and every fluctuation becomes clear. But the universe expands, structures shift, energies dissipate, And the deeper you try to look, the more the system changes beneath your gaze. Knowledge is always chasing a moving horizon. There is also the holographic boundary, a quiet rule hidden in physics that says the maximum information inside any region of space is determined not by its volume, but by the surface that encloses it. A strange and gentle truth. It means the universe never allows infinite detail in a finite space, never allows information to grow without limit, never allows a perfect description of every particle and every interaction all at once. There is always a ceiling, a soft informational horizon that gently limits what any observer can know. Imagine a sphere filled with matter, energy, and fields. The amount of information inside it cannot exceed the number of tiny bits that could be painted onto its surface. The boundary decides the content. The edge defines the interior. A quiet reminder that limits surround us in ways both subtle and profound. There is another limit woven into the heart of complexity. The more intricate a system becomes, the harder it is to predict. A single particle can be described with calm precision. A billion particles can still be understood through the mathematics of fluids and thermodynamics. But the moment those particles begin to interact in nonlinear ways, the moment patterns feed back on themselves, the moment new structures emerge, prediction begins to fail. Chaos is not randomness, it is sensitivity. It means that tiny differences grow quietly, then suddenly until prediction becomes impossible. Not because the system hides its rules, but because the rules amplify the smallest fluctuations beyond all ability to foresee. This, too, is a limit of knowledge, a reminder that even in a universe governed by precise laws, the future can remain unknowable. Not because reality is vague, but because its richness outpaces the reach of any mind or machine trying to follow it. There is also the limit of perspective. We look outward from inside the universe. We are part of the system we are trying to understand. And any system describing itself faces constraints. A book cannot contain a perfect description of every detail of the book itself, and also remain the book. A circle cannot hold its center and its circumference and the entire plane around it inside itself without losing its identity. An observer cannot step outside the universe to see the whole. So our understanding will always be partial, always nested within what we hope to comprehend. This is not a failure. It is simply the gentle shape of what it means to be an observer. Another limit comes from the principle that to compute every detail of reality would require resources as large as reality itself. A perfect simulation of a universe would need the same amount of information, matter, and energy as the universe being simulated. Anything smaller must approximate, simplify, let go of perfection. So no mind, no machine, no cosmic intelligence could ever compute the full multiverse down to every microscopic detail unless it was as vast as the multiverse itself. And once it becomes that vast, it is no longer a model, but simply another universe. Knowledge and existence fold together. The boundary between them softens. There is also the limit of light itself. Information cannot travel faster than the speed of light. No signal or message or measurement can outrun that constant. So there are parts of the universe that will remain forever beyond reach, not because of distance but because of time. Their light will never reach us. Their events will never cross our sky. They drift in permanently unreachable regions, silent and self-contained, an entire branch of the cosmos that will never be observed, not even in principle. And if the universe expands forever, the number of unreachable regions will grow without end. Knowledge shrinks relative to what exists. What we can see becomes smaller with every passing epoch. Yet inside this shrinking bubble, meaning persists, curiosity persists, wonder persists. The limits do not take them away, they frame them. There is also a subtler boundary, a limit on what can be defined with absolute precision even in theory. Some questions cannot be answered because the question itself cannot be made precise enough to have a single true answer. Is time continuous or discrete? What is a law of nature beyond the mathematics that expresses it? Is the universe ultimately deterministic beneath the layers of probability? These questions drift at the edge of definability. Their answers may exist, or they may not exist in any clean final form. This, too, is a limit of knowledge, the limit of what can be asked in a meaningful way. What cannot be framed cannot be resolved. There is also the emotional horizon, a quieter one, a limit not of physics but of the mind. Past a certain depth of complexity or scale, the brain cannot hold the full structure of the concept. Infinity of infinities, hierarchies of universes, dimensions folded beyond imagining, they exceed the architecture of our cognition. Not in a discouraging way, but in a peaceful one. The mind reaches far, then glides gently into a space where it no longer tries to grasp everything. It simply rests in the immensity of possibility. This is its own kind of understanding, not the kind of knowing measured in equations, but the kind measured in stillness. At the deepest level, there is the limit that some truths may simply never interact with us. There may be universes whose laws never overlap with ours in any measurable way, structures forever hidden because nothing about them affects anything here. They exist in the great tapestry of all that is possible, but they cast no shadow on our sky. And because knowledge requires interaction, requires signals, requires some thread of influence, these universes remain beyond all reach, not because they are far or faint or quiet, but because they are disconnected in principle, absolute horizons in the landscape of existence. Yet their presence, even as a concept, expands the mind and invites a soft, tranquil humility. There is also the practical limit of time. Civilizations rise, fall, transform, forget, rediscover. Even if knowledge expanded without bound, the species gathering it may not last long enough to reach every truth. The universe itself may not last long enough. Stars will cool, galaxies will thin, entropy will increase, and even the tools of measurement will fade. Long before every truth is uncovered, the cosmos will grow cold and quiet. Knowledge is a race against the lifetime of everything, and yet this limitation gives meaning to the search, a gentle urgency woven into curiosity, a soft reminder that knowing is a temporary gift in an impermanent universe. And with all these limits woven around us, the question arises, why search at all? Why reach into the unknown when so much will remain beyond reach? The answer is quiet and simple, because understanding is not only about answers, it is about deepening our relationship with the universe, with the mystery that surrounds us, with the feeling of being a conscious presence inside something vast. Knowledge is not only accumulation, it is connection. The limits do not diminish that connection. They sharpen it, soften it, give it shape. The horizon makes the sky more beautiful. The ocean's edge makes the sea more powerful. The limits of knowledge make curiosity a kind of meditation, something to rest inside rather than conquer. The multiverse, with all its vastness and silence and unreachable realms, becomes a place not only of speculation but of gentle reflection, a reminder that we inhabit a single thread in a tapestry beyond imagining, and that the limits of what we can know are not walls but windows through which wonder quietly enters. There is a quiet truth that becomes clearer the deeper we wander into the idea of limits. The universe is not trying to hide anything from us. It is simply structured in a way that makes certain questions unanswerable, not out of secrecy, but out of nature. This realization changes the feeling of the unknown. It becomes less like a locked door and more like a horizon seen across calm water, a place you can look toward but never stand upon, a place meant to be admired rather than crossed. And yet there is meaning in looking. One of the most profound limits is the one placed by the finiteness of human perception. Our senses evolved to navigate the scale of everyday life, the distance of a few steps, the weight of a stone, the brightness of the sun filtered through an atmosphere. But the universe is filled with structures that lie far outside these ranges, distances that stretch for trillions upon trillions of miles, energies too high for any human-made detector, waves of space-time so faint that even colossal instruments barely notice them. We see only a sliver of what is. Our senses are tiny windows opening onto an ocean, and even with telescopes and detectors and vast computational tools, our window remains small. This limitation is not a failing. It is part of the beauty of being a finite creature inside an infinite expanse. The wonder comes from the scale we cannot fully reach. Another limit comes not from the universe, but from logic itself. There exist statements that cannot be proven or disproven within any given set of rules. This was revealed by the deep mathematical insight that even a perfect logical system cannot prove every truth about itself. There will always be truths that remain outside the reach of proof. This is not a flaw of mathematics. It is simply how consistency works. And if mathematics contains unprovable truths, then any scientific theory built on mathematics may also contain questions that cannot be resolved from within the theory. Some aspects of the multiverse may live in this space. Not false, not true, not undecidable out of complexity, but undecidable in principle. A quiet category of questions that rest beyond resolution, and yet their presence does not diminish the value of investigating them. It simply means that exploration may matter more than conclusion. There is also the limit created by the very structure of physical law. Some constants are measured values, not derivable from deeper principles. The strength of gravity, the mass of the electron, the speed of light, the dark energy density. These may not have fundamental explanations within our universe. They may simply be the parameters of this particular cosmic region. And if other universes exist with different constants, those differences may be forever beyond our ability to test. We can imagine them, calculate their consequences, analyze their stability, but we may never see even the faintest shadow of their presence. This, too, is a limit of knowledge, a reminder that some answers depend on access to regions of existence beyond our reach. There is a subtler limit woven into quantum reality. To know a system precisely requires isolating it from everything else. But isolation is nearly impossible. The universe is a web of interactions, particles jostling, fields overlapping, waves interfering. Every measurement is a disturbance. Every disturbance spreads outward. Perfect knowledge would require perfect isolation, and perfect isolation would require disconnecting a system from the rest of the universe. And nothing in the universe is ever fully alone. So perfect knowledge remains forever out of reach. But the softness of uncertainty is not a flaw. It is a feature of quantum reality. It allows the universe to remain dynamic, fluid, alive with possibility. If everything were knowable with absolute precision, the world would be static, motionless, without creativity. Uncertainty is the quiet engine of change. There is also the limit that arises from the nature of time. Time may not be fundamental. Some theories propose that time is emergent, rising from quantum entanglement or statistical behavior of deeper structures. If time itself is not a basic ingredient of reality, then understanding it fully may require stepping outside of our temporal intuition. But we cannot step outside time. We think in sequences, we remember past states, we anticipate futures. Our awareness is anchored in the flow. We cannot perceive a timeless universe as it truly is. This limit is not intellectual, it is experiential. Our consciousness is woven into time too deeply to ever escape its structure. This leaves regions of deep theory partially obscured, concepts that cannot be held within the framework of beings who live in sequence. A quiet boundary between what exists and what can be comprehended. Another profound limit comes from the asymmetry between what can be detected and what can be inferred. We often infer far more than we directly observe. The existence of dark matter, the shape of space-time, the birth of the universe, the distribution of galaxies, the behavior of particles too small to see, all of this is based on inference, and inference requires assumptions. Most assumptions are well-motivated, carefully tested, deeply grounded in evidence. But at the deepest levels of cosmology, assumptions become subtle, often tied to the very structure of what counts as an observation. We may never know with total certainty which assumptions are universal and which are local to our cosmic environment. This introduces limits not from data scarcity, but from the nature of interpretation. Even with infinite information, some truths may remain indeterminate because multiple explanations fit all possible data equally well. Reality may contain ambiguities that cannot be resolved even with perfect observation. A quiet kind of unknowability, not born of ignorance but of structural symmetry. The limit of scale adds another boundary. At very small distances, near the Planck length, our theories break down. Space-time may not be smooth. Particles may not be localized. Geometry itself may flicker like a quantum cloud. And at very large distances, near the cosmic horizon, space-time stretches in ways that distort what we can infer. Between these extremes lies the realm we can describe clearly. Outside them lies a region where our best theories become approximations or metaphors. Not false, but incomplete. Not incorrect, but insufficient. A gentle boundary where mathematics meets the unstructured depth of reality. There is also the psychological limit embedded within complexity. The more abstract a concept becomes, the harder it is to maintain it in working memory. The brain was not shaped to store multiverse geometries or 11-dimensional brains or infinite ensembles of cosmic variation. Yet we reach toward these ideas. We hold them for moments at a time before they slip back into the mist. This slipping is not failure. It is the natural rhythm of a finite mind touching infinite possibilities. The concepts drift in, open a moment of wonder, then drift out again, leaving a quiet echo. And that echo is often the part that matters most. There is also the temporal limit imposed by the universe's evolution. We live in a specific cosmic era, a time when stars still shine, when galaxies remain clustered, when the cosmic microwave background still carries information about the early universe. But trillions of years from now, that background will fade, galaxies will drift apart beyond visibility, and cosmic information will be harder to extract. The ability to know declines with time. Future civilizations may know far less about the origin of the universe than we do now. Not because they are less advanced, but because they exist in a dimmer cosmos. Knowledge is influenced by when you look, another quiet limit woven into the structure of cosmic history. There is also the horizon of interaction. To know something in a physical sense requires exchanging energy or information with it. But if a region of space never interacts with ours through gravity or light or quantum fields, its existence remains undetectable. There may be entire realms that remain forever silent, not because they are distant, but because they share no interaction channels with our universe's laws. A multiverse filled with quiet pockets of reality forever inaccessible. And though we can imagine them and predict their possible forms, their presence rests at the edge of conceptual knowledge. Not beyond existence, only beyond contact. Another limit comes from the complexity of initial conditions. Even if we understood the laws of physics perfectly, predicting the full evolution of the universe would require perfect knowledge of its starting state. But the starting state may contain detail far too fine-grained to ever reconstruct. Some information may have been erased by entropy, some scrambled beyond recovery, some never knowable because it existed before time itself emerged in its current form. The past contains depths that cannot be revisited. Not for lack of curiosity, but because the universe does not keep a perfect diary. Some pages are smudged or missing or written in scripts that no longer exist. This too is a limit, a gentle one, a reminder that origin stories contain mysteries that cannot be fully restored. In the end, the limits of knowledge do not diminish the universe. They give it shape. They create the space in which wonder can exist. If everything were knowable, the universe would feel smaller, flatter, emptier. It is the unknown that gives depth to the night sky. It is the unreachable that gives meaning to the quest. It is the unprovable that gives beauty to the idea of possibility. The multiverse is not only an idea about many worlds, it is an idea about the limits of knowing a single one. And within those limits there is room for contemplation, humility, imagination, and a quiet unfolding of perspective. The unknown is not a darkness. It is a soft expanse where the mind can drift without boundary, a place where thinking becomes dreaming, and dreaming becomes understanding in a gentler form. There is a limit woven into the nature of identity itself. To ask whether another version of you exists in some distant region of an infinite cosmos is to ask a question that depends on definitions the universe does not enforce. Are you the arrangement of atoms, the flow of thoughts, the history of choices, the pattern of consciousness, the continuity of memory? In an infinite multiverse, all of these could reappear in some distant region. But would that really be you? The universe does not answer this. Identity is a human construction, a useful one, but not one written into the mathematics of cosmology. Physics traces the evolution of states and systems. It does not assign meaning to the thread of consciousness that observes them. This is another quiet limit. Not because the universe is vague, but because consciousness is not a parameter in the equations. It is something emergent, something that arises from structure and complexity and neural activity, something that the laws of physics do not classify the way we classify it. So the question of another you exists in a boundary zone, half mathematical, half philosophical, neither fully answerable nor meaningless. a mystery that lives in the space between objective law and subjective experience. There is also the limit created by the asymmetry between local knowledge and global truths. We know our region of space-time with some clarity. We understand the physical laws operating around us. We measure particles, fields, forces, curvatures, but the global structure of the universe may be forever inaccessible. Is the universe finite or infinite? Does space wrap around in higher dimensional shapes? Are there regions with different physical laws? Does the cosmos branch at quantum boundaries? Is reality encoded on a distant horizon? These are global questions, and global questions require global access. But we inhabit a small and finite region bounded by a cosmic horizon beyond which no light will ever reach us. Everything outside that horizon is disconnected from our observational reach. This means any global description of the universe rests on extrapolation, on extending local rules far beyond the region in which they can be tested. Most of the time, this is reasonable. Physical laws appear uniform on vast scales. But uniformity is not guaranteed beyond the horizon, so our ability to know the whole is limited by our confinement to a small part. The universe may be vast, infinite, filled with regions stranger than anything we can imagine, but we see only a drop from an ocean, a gentle constraint, a soft reminder of perspective. Another profound limit emerges from entropy. As the universe evolves, entropy increases. Information becomes dispersed, structures break down, thermal noise grows. This process erases detail, not metaphorically, but literally. The early universe contained information about initial conditions and microscopic variations. Over billions of years, much of that information has been diluted, scrambled, spread out beyond recovery. Even with perfect instruments, perfect models, and infinite time, certain details are irretrievably lost. Entropy places a fundamental limit on how much of the past can ever be reconstructed. The deeper we look into the earliest chapters of the cosmos, the more we find pages that have faded beyond recognition, not because they were never written, but because the universe does not preserve everything. Some stories are lost to time in the most literal sense, and in that loss there is a quiet kind of beauty, a reminder that impermanence is part of the cosmic fabric. There is another limit that arises not from the universe but from us. Our models are created by human minds. We use mathematics to describe patterns, we use logic to connect those patterns, and we use intuition to interpret the meaning. But intuition is shaped by evolutionary history. We evolved to model objects thrown through the air, to navigate terrain, to predict the behavior of familiar creatures. Our brains are not naturally shaped to understand quantum fields, hyperbolic geometries, multidimensional brains, or infinite ensembles. We can reach toward them, with effort, with abstraction, with layers of reasoning, but we cannot inhabit them the way we inhabit the intuitive world. This gap between intuition and mathematical truth creates another limit. Some aspects of reality may simply resist intuitive visualization. We can calculate them, simulate them, prove them, but never truly picture them. A gentle boundary between what is physically real and what is mentally accessible. And this boundary is not a failure of the human mind. It is an invitation to humility, a reminder that we can understand without imagining, that truth may not always feel like something our senses were built to hold. Another boundary comes from the structure of scientific method itself. Science proceeds by falsification, by testing predictions, by eliminating theories that contradict evidence. But if a theory makes predictions that cannot be tested because the relevant phenomena lie beyond our horizon or unfold across realities we cannot access, then that theory may never be falsifiable. This does not make it worthless. It simply means it belongs to a category of frameworks that explore possibility rather than answerability. Some multiverse models lie in that category. They explain why physical constants take their observed values, or why inflation behaves as it does, or why quantum systems branch into outcomes, but they may never produce observable differences that separate them from competing ideas. This is a limit imposed by the structure of testing itself, not a limit of imagination, or logic, or mathematics, but a limit of what counts as scientific evidence. And yet these ideas can still shape understanding, still guide inquiry, still offer meaning in the search for frameworks that fit the universe, even if they cannot be proven or disproven in the traditional sense. a boundary between testable reality and conceptual possibility. There is also the limit created by cosmic variance. We observe only one universe, only one realization of initial conditions, only one pattern of fluctuations, only one arrangement of galaxies. If multiple universes exist with different conditions, we cannot compare ours to others. We cannot gather statistics over many universes. We cannot measure how typical or atypical our cosmos is. With only one sample, some questions have no clear answer. Is our universe fine-tuned? Is it common? Is it rare? Is it inevitable? Cosmic variance makes these questions intrinsically limited. We can simulate possibilities, analyze probability spaces, study distributions, examine physical landscapes, but the universe offers us only one data point. And a single data point cannot reveal the full structure of a population. This is another limit, soft but fundamental. Not a barrier to exploration, but a boundary around certainty. Another limit comes from the future. As dark energy drives the expansion of the universe, the cosmic horizon grows. More galaxies slip beyond visibility. Light from distant clusters never reaches us. The observable universe shrinks in communicable terms. Even as the total universe may expand without bound, the future contains a quieter sky. And with a quieter sky comes less information. A limit slowly tightening with time. In tens of trillions of years, future observers may see only a single galaxy, isolated, surrounded by darkness. All evidence of the Big Bang, cosmic structure, and the larger universe will fade beyond reach. Even with perfect technology, their knowledge will be bounded by the emptiness of the future cosmos. So the ability to know is influenced not only by what exists, but by when one lives. A poetic limit, a temporal horizon as real as any spatial one. Another boundary lies in the relationship between truth and usefulness. Not all true statements are meaningful for scientific description. Not all possible details matter for explanation. Some truths are simply inaccessible, and some are irrelevant to prediction or carry no consequence for observable phenomena. This creates a conceptual limit. The universe may contain far more complexity than is needed to describe its behavior, or far less. We may never know which details are essential and which are extraneous. In the multiverse context, this becomes profound. If many universes exist with different laws, the space of possibilities may be enormous. But only a small subset may produce structures, galaxies, chemistry, life, and only an even smaller subset may be relevant to the explanation of our own universe. The rest may be mathematically real, but scientifically silent, a quiet limit between existence and relevance. The final limit may be the most profound. There is a boundary between knowledge and meaning. Science can describe the structure of the cosmos, the laws that govern it, the probability landscapes, the origins of matter, the behavior of fields, the evolution of space-time. But meaning is not part of physical law. Meaning is something we create. The universe offers structure, patterns, regularities, phenomena, but it does not tell us what these patterns signify for consciousness or purpose or belonging. We must decide how to interpret the immensity we inhabit, and that interpretation is shaped by wonder, curiosity, and the desire to make sense of our place within something vast. This limit is not a barrier. It is an opening. The unknown is not empty. It is spacious. It is gentle. It is a field where imagination and reason meet without conflict. A place where the question, what is real, becomes intertwined with the question, what does it mean to exist inside reality? This is the quiet frontier where science meets reflection, where knowledge meets humility, where the universe meets the mind. There is a gentle truth beneath all of these limits. The universe does not promise us completeness. It does not guarantee that every question we ask will have an answer we can reach. But it does offer something else. It offers a relationship between curiosity and reality, between the questions we form and the structures we find, between the smallness of a human mind and the vastness of a cosmic landscape that may contain countless worlds. In that relationship, the limits of knowledge are not a rejection. They are a kind of frame. A frame around the painting, a shoreline around an ocean, a boundary that makes the experience of wondering possible. If we knew everything with perfect clarity, if every question had a closed and tidy answer, there would be no room for the quiet joy of not knowing, no room for the soft suspense of possibility, no room for the peaceful feeling of standing at the edge of a mystery and simply letting it exist. The multiverse, whatever its ultimate reality, brings this feeling into sharp focus. It reminds us that the totality of existence could be far bigger than the part we see, that there may be universes whose laws we will never know, branches of reality we will never inhabit, dimensions we will never move through, and yet our own experience is still complete in its own frame, a finite life inside an infinite possibility, a single thread inside an ungraspable tapestry. So the limits of knowledge invite a certain posture, not denial, not resignation, but a soft humility. A way of saying this is as far as we can see, and beyond this is a region of quiet openness, a region where many models are possible, where several explanations may coexist, where the question remains larger than any one answer. In that region, the multiverse becomes not a checklist of scenarios to confirm or reject, but a meditation on how reality might overflow our concepts. A reminder that our best theories are still approximations, maps drawn from inside one small corner of a vast terrain. We refine them, correct them, stretch them, but somewhere beyond their reach, the landscape continues. It does not end where our mathematics runs out. It does not collapse because our instruments cannot follow. The cosmos goes on, quietly, with or without our comprehension, and there is a strange comfort in that, a calm sense that the universe does not depend on our understanding. It simply allows us to participate for a little while, to notice, to think, to feel awe, and then to rest. At the deepest level, the limits of knowledge show us something gentle about ourselves. They reveal that our desire to know is not only a tool for survival, but a form of connection. When we ask whether other universes exist, whether physical laws can vary, whether reality branches, whether space is infinite, we are also asking a subtler question. We are asking what it means that we are here at all. We are asking how to situate this brief consciousness inside something so far beyond it. We are asking whether this moment is an accident, a necessity, a rare fluctuation in a cosmic sea, or simply one expression of a deeper structure that we may never fully see. The answers may remain incomplete, the data may remain sparse, the theories may remain in tension. Yet the act of asking shapes the way we live. It encourages patience, curiosity, and a kind of gentle courage. The courage to walk to the edge of the knowable, to look beyond, and to accept that the horizon will always stay ahead of us, receding as we approach. There is no final vantage point from which everything is clear, but there is this present vantage point, this moment of awareness, this simple act of breathing in the dark and letting the universe be mysterious. And that is enough. As these reflections on the limits of knowledge come to rest, you can imagine yourself standing again on the shore of that quiet cosmic ocean. Behind you are the paths we have walked tonight, through inflationary bubbles and quantum branches, through strange landscapes of changing physical laws, through infinite space and repeating patterns, through brains and higher dimensions, through simulations and emergent realities, through horizons and the boundaries of what can be known. Before you is the open sea. You do not have to cross it. You do not have to chart it. You only stand and listen to its soft presence, noticing that it is there, noticing that you are here, and feeling that the relationship between the two does not need to be solved tonight. It can simply be felt. Now, as the exploration of possibility and limits gently loosens its grip, you can feel another movement begin, a slow turning from questions toward rest, from maps toward silence, from the branching structures of thought toward the simple fact of being here. You have wandered through many worlds in imagination. You have drifted through landscapes of theory and wonder. Now the multiverse can soften, not as a problem to be calculated, but as a backdrop for sleep, a quiet canvas stretching beyond view upon which this universe, your universe, is painted as one tranquil scene. You are part of that scene, a small region of awareness, nestled inside a vast and gentle unknown. As the epilogue begins, you might picture all of the possible universes we have spoken of tonight, not as sharp diagrams or long equations, but as distant lights in a calm night sky. Each light is a different way reality could unfold. Some glow faintly, barely structured, their laws too fragile to build stars or life. Some shine with wild and exotic physics, dimensionalities and interactions utterly unlike our own. A few glimmer with familiar patterns, galaxies swirling, stars burning, planets cooling, molecules forming, chemistry weaving toward complexity. And within one tiny light, one small possible universe, there is a spiral of stars we call a galaxy. And inside that galaxy, a modest star, and around that star, a rocky planet, and on that planet, a thin film of life and thought, and within that film, you. If the multiverse exists, this is one story among uncountably many. If the multiverse does not exist, this is still one story among all the ways matter and energy could have been arranged and did not arrange themselves. Either way, the fact that you are here experiencing this moment, listening to these words, breathing, feeling the weight of your body, the softness of fatigue, is a quiet miracle of contingency. Not an impossible miracle, not a breaking of laws, but a gentle alignment of conditions and histories and probabilities that needed to coincide for this simple moment to be real. You lying here at the end of the day. You resting in a universe that might be one among many. You do not need to decide which picture of reality is true. You do not need to choose between branching worlds and infinite space, between cosmic landscapes and brain collisions, between simulations and emergent patterns. Tonight, these possibilities can drift around you like distant constellations. Interesting, beautiful, but far away. Their purpose now is not to demand attention, but to soften it, to give your thoughts something vast and gentle to float upon, so that the smaller concerns of daily life, the sharp edges of worry and memory, can gradually dissolve into something larger. The multiverse in this quiet sense is not a technical claim. It is a lullaby about possibility, a way of whispering that whatever the ultimate structure of reality may be, you belong to something spacious, something that can hold your questions, your hopes, your uncertainties without strain. As your breathing slows, you might imagine all the possible versions of this very night. Worlds in which you did not press play, worlds in which you chose another story, worlds in which the details of your day were slightly different. Or you might not imagine anything at all. You might simply notice the gentle rise and fall of your chest, the heaviness of your limbs, the way thoughts begin to lengthen, to blur at the edges, to stretch out like fading ripples on a very still lake. In that soft blurring, the boundaries of the day begin to loosen. You are no longer in the bright, sharp world of tasks and decisions. You are in a twilight region, between waking and sleeping, between focused thought and drifting images. This region is its own kind of universe, a small personal cosmos where memories, dream fragments, feelings, and impressions float past without the need to be organized. You can let them pass. They do not need to be understood or controlled. They can simply move like clouds across a darkening sky. Somewhere beyond all possible worlds, beyond all models and diagrams, there is the simple fact that you are tired and that rest is allowed. In a universe governed by laws, described by equations, filled with galaxies and particles and horizons, there is also this ordinary softness. The softness of a human being at the end of a long day, choosing to lie down, to close their eyes, to release their thoughts, and to trust that the world can continue without them for a while. The stars will keep moving, the galaxies will keep drifting, the cosmic microwave background will keep cooling. If multiple universes exist, they will go on in their silent trajectories. You do not have to hold any of this. You can let it go. You can let the entire multiverse recede to the background, like a vast dark theater in which the lights are slowly dimming. The stage of awareness grows quieter, until only a few small lights remain. Then fewer. Then none. Only darkness. And the soft continuity of sleep. As you approach that darkness, remember that not knowing is not a failure. It is a natural state. For most of cosmic history, there were no questions. There were only processes, fields, particles, expansions, collisions, happening without being witnessed. The fact that questions have appeared at all, in one corner of one universe, inside minds like yours, is already a remarkable development. It does not need to be completed or perfected. It simply is, a brief phase in the life of the cosmos, where matter learns to ask about itself, and then, like everything else, to rest. So as this narration draws towards silence, you can imagine that all the topics we have touched upon tonight, the birth of universes, the branching of realities, the shifting of physical laws, the repeating patterns of infinite space, the hidden dimensions and drifting brains, the simulated structures and emergent rules, the limits of observation and knowledge, all of them are slowly being set down. Like books closed gently on a quiet table, they remain there, available, if you ever wish to open them again. But for now, the table is still, the pages are closed, the questions are resting, the universe is allowed to remain mysterious, and you are allowed to sleep. Breath by breath, thought by thought, you drift away from the bright shore of waking awareness into a softer ocean of dreams, where worlds can rise and fall without effort, where laws of physics can bend into stories, where possibilities can play without needing to be proven, where your mind finds its own multiverse of images and feelings, and then beyond even that, into deep, quiet sleep, where there are no questions, no models, no horizons, only rest. Let the multiverse of waking thoughts fade now into the stillness of one simple universe in which you are peacefully asleep.